My name is Brian Pearson, and I serve as head of business development here at qBraid, and we'd love to welcome you all today to the Quantum Developer Day 2025. Yeah, woo! Thank you all. Thank you all. Um, I know many have traveled here very far from across the country. We have about 300 virtual attendees from across the world tuning in, so waving to them now. Want to emphasize that today is much about collaboration. We're going to talk about platforms, modalities, and academic disciplines. And so to start us off, I'd love to welcome Kate Timmerman, CEO of the Chicago Quantum Exchange.
Thank you, Brian. I'm just here to say thank you guys for coming. To the point of collaboration, this is a phenomenal partnership. qBraid and CQ have been collaborating for years now. I'm really excited that the Developer Day is kind of the first event in the physical space that we will be hosting the Chicago Quantum Summit tomorrow and on Tuesday. And have a great day. Learn lots of cool things. And I also look forward to Quantum Developer Day 2026. Awesome.
Thank you so much, Kate. And so today we're bringing together developers, researchers, and industry leaders to exchange ideas, share some of the breakthroughs that they've made throughout the year, and then ultimately we will define the future of quantum software together. And so on behalf of qBraid, I want to give a huge, huge thank you to all of our sponsors and partners, IBM, IonQ, Rigetti, Xanadu, Quantum Machines, Quantum Rings, Unitary Foundation, and Q-Control. It's fantastic. We really have a packed house here. And I also want to recognize some of the support from our professors at the University of Chicago and UW-Madison. Thank you for taking the time on this Sunday afternoon to speak more on some of your research and work, as well as the CQE, of course, and finally, the Illinois Quantum and Microelectronics Park, a truly, truly groundbreaking facility being built just 10 miles south of here. So it is my pleasure to now introduce our keynote, The Future of Quantum Software. Please put your hands together for Kanav Setia, co-founder and CEO of qBraid.
All right. Thank you so much for showing up on a Sunday afternoon. Last time we did an event on Friday evening, and we were told, please don't do event on Friday evening. So next option, apparently, we chose was Sunday afternoon. we probably end up using all of our brain developing quantum software and not too much left planning event. Okay, so thank you so much for being here. Today, we're announcing the next generation of qBraid platform and sharing our vision for the future of quantum software. This platform is designed to accelerate the pace of innovation in quantum industry and push the boundaries. Quantum software has this layered structure, and all of those layers are constantly evolving. This means you end up with a lot of pain points such as installation issues, dependency conflicts, and there's like so many different SDKs and connection to hardware you have to manage yourself. So this leads to slowing down even the best of the developers. So when we started out in 2020, we started out with a simple mission. Developing of quantum software should be easy. It shouldn't be hard. Our goal was to give researchers and engineers a seamless in-browser experience where they can just log in and get access to a sandbox environment that provides them access to all the different quantum software which are ready to go. Over the years, we've integrated a whole bunch of SDKs in one place, added so many different QPUs, and more recently, we've also added a whole bunch of GPUs as well, clusters of GPUs. You can just log in, get access to all the software that is out there, and along with GPUs from NVIDIA, and yeah, quantum computers from many more companies as well. This has attracted a lot of interest in our platform, from classroom workshops to industry R&D use cases. qBraid has become the hub where quantum development happens. accessible, unified, and ready out of the box. Today, qBraid users represent over 120 countries, over 500 academic and research institutions, over 200 enterprise companies, and we have over 15 SDKs and over 25 QPUs and simulators available on our platform. As per independent survey done by Unitary Foundation under their quantum open source survey, we were at 14.2% of the user market last year, and we're excited to find out what the number would be this year. And this is just the beginning. Our mission remains unchanged to accelerate the innovation in quantum industry. We began by empowering a single persona, quantum developer, but our platform has grown far beyond that. End users want to learn and build. Enterprise companies want to train their teams and deploy applications. QPU companies want to connect their hardware to users worldwide. Today, we're announcing new tools that bring all of these worlds together. These tools are built on the same foundation that made qBraid loved by developers all over the world. There are three main announcements. First, we're announcing the next generation of our platform. This is our biggest upgrade yet. We've reimagined the platform from ground up to make everything faster, smarter, and more connected. It comes with many big updates, many more capabilities, but the same simplicity of qBraid. The platform is designed to meet you where you are. You will have access to qBraid tools both on your local computers as well as cloud. And you will have easy access to a whole bunch of GPU clusters, QPUs, seamless integration with various cloud providers. So if you have a whole bunch of different accounts, you can bring them to qBraid very easily. And we're also going to be providing integration with many AI tools. The platform now has integrated access to AI agents, which are natively available, that will be there to help you out through your quantum journey. Next, we're excited to announce agentic workflows and orchestration. Imagine working on a complex problem that requires testing out a whole bunch of different techniques to see which of them work and which of them don't work. Now imagine supercharging the exploration with assistance from agents, where each agent is working on one of the techniques, all of them working in parallel, getting you the answers to select which one of them works well. We envision that you will work with the main agent, come up with a plan, and submit it to a whole bunch of agents on qBraid. There will be an orchestrating agent with access to many sub-agents. And the sub-agents, the orchestrating agent is where you will submit your complex plan, which can then submit and distribute tasks to sub-agents, which will then have access to various QPUs. And these sub-agents report back their aggregated output to the orchestrating agent, which then will give you the answer or give the answer, compiled answer to your AI assistant. We've designed strong guardrails to keep you in control. Every action is transparent and every decision is yours. So agent will not do anything without your permission. So that was the second bit. The third is we're announcing qBraid OS. qBraid OS is meant to bring the simplicity of qBraid to QPU companies. It's designed to handle all the software requirements for you. It is aimed at providing QPU companies customer with vertical integration like experience. In this architecture, you can see qBraid Gateway handles the scheduling, network configuration. Runtime is where the task distribution to GPUs, QPUs, CPUs happen. And qBraid SDK is where the end users will build quantum algorithms. qBraid runtime and gateway together form something we're calling qPod, which is meant to live closer to the raw compute. Whereas qBraid SDK is meant to live very close to the end user, where it'll live on their local computers, where they will develop a whole bunch of algorithms and then submit to various qPods. qBraid OS is designed to put your quantum computer on cloud without hassle and roll it out to your users around the world, or you can even keep the access to your quantum computer limited to certain organizations or just your organization for testing purposes. To enable all of the three things that I just mentioned, we're announcing many more partnerships. These build upon the partnerships we already have, and you will hear about many of the partnerships in a brief demo that I will do in a little bit. So I'd like to close my presentation part of the talk with our vision for future of the quantum software. We envision the compute pipeline to look like so, where users are building their quantum algorithms in qBraid SDK. And then through qBraid SDK, that sends out a whole bunch of tasks to various qPods, which then orchestrate the smaller subchunks to QPUs, GPUs, CPUs without much of a problem. And our goal is to actually merge this computational orchestration with the agentic workflow. So essentially, we want to meet people where they're at. That means if you don't have a whole bunch of quantum algorithm background, you will be able to use this agentic framework and access this compute orchestration pipeline. So even if you are a subject matter expert but do not have strong background in quantum algorithms, you'll just be able to design the computational workflow pipeline by talking to an agent. So with that, I want to give you a glimpse of what the future of quantum software looks like, and I'm going to be giving you a quick demo. So this is what our new and improved platform looks like. We've tried to put everything you're going to need on this dashboard. So you can see there are now many more compute profiles that you can launch. Some of you who use qBraid regularly, you'll see this is a little bit familiar to what you use on qBraid already. So whether you want to use Intel's Quantum SDK, QRS blockade, or run massive simulations with high qubit numbers using NVIDIA's CUDA Quantum or IBM's Qiskit Air on a cluster of NVIDIA Blackwell GPUs, it's all here one click away. Down here, you'll see there's an overview of your quantum jobs. On the right-hand side, there's recent activity, the notebooks you were working on. There's a whole bunch of quick actions where you can launch AI assistants. And down here, there's some trends for the past usage of the platform. So it's meant to give you an overview of like your quantum workflows trends in one place. So now I want to move on to devices, which has gone through a big update as well. It now provides you with a much richer experience with much more information. Whether you want information about the qubit count or information about how to get started, it is all here in one place, and it'll make it easier to test out many more devices as time goes by. Further, you'll see this page evolved rapidly as many more quantum computers show up, especially with the introduction of qBraid OS. Let's say you try out a whole bunch of quantum computers. This is where you'll find all your jobs. We have now a very nice overview page, and you can find all your stats for jobs in one location. Let's say you want to look for one particular job. We've added many more filters and tried to provide you many more deeper insights all in one place. It makes this UI makes it very easy to find your job, past job that you might have submitted a little bit ago. Then on the learn side is where it has also gone through an upgrade. You can find all your courses in one location. And this is where you'll hear more about our collaboration with Q-Control. We'll be announcing many more courses on this platform. So shout out to Mick, who'll be doing a quick walkthrough of the Q-Control and qBraid partnership. Then we are introducing many more features targeted at the enterprise world, where managing all your users in one location and their access to various quantum resources or classical resources has gotten easier than ever on qBraid. So there's so much that we built into this platform, but what I really want to share with you is the coolest feature that we're building. This is our AI assistant. Let's say you're starting out in the quantum world. What this AI can do for you is you can come here, you can ask it questions about, hey, how do I get started in quantum? Not only it'll give you guidance on quantum computing, but it knows so much about our platform as well. And it just doesn't stop at the information. What's incredibly cool about our integration is this AI is deeply integrated with the entire qBraid platform. It can take a whole bunch of actions on your behalf. So for example, let me show you, I can go here and type, hey, can you get me my past 10 quantum jobs and explain what they were. So you'll see it fetches the data of my past 10 quantum jobs. It lays them out very nicely and then can guide me through what jobs I had submitted. And it also tells me like a whole bunch of overview information that could be very useful. So we've been playing quite a lot with various quantum computers. You can see preparing for this demo, IQM Garnet, Rigetti Zanka 3, and some jobs failed. I think IonQ should be here as well. And so it guides you through what jobs has succeeded, what have failed, and then it can also allow you to submit jobs. Can you build a GHC circuit and submit it to Rigetti, IonQ, and IQM. So what you're going to see is it analyzes the request, it gets all the data that it's going to need to submit a job, and then asks me for the permission. Perfect. Okay, let's try one more time. Can you actually just build chasm for GHC and then directly submit it? Perfect. So you can see it's asking me for approval. Boom, boom, boom. Now it should be getting back to me and saying, hey, all the jobs have been submitted. So this makes access to quantum computers incredibly easy for people who don't have much background in quantum computing. So a lot of the subject matter experts in the enterprise world, they can start using and playing with these machines incredibly easily. Then a little bit glimpse of what is to come in the agentic framework is I can actually get a much cooler prompt. I think I had it somewhere here. Let me bum, bum, bum. Let me grab this. So here what I'm going to do is I'm going to ask it to make a QDD agent demo directory in my home directory. generate detailed instructions for an agent to build and run 5-qubit noisy quantum volume circuits using IBM Qiskit and NVIDIA CUDA Quantum, apply noise models from any IBM quantum machine, and then compare runtimes, and then put a description in what it did in qv.md. And you'll see it just goes ahead, comes up with instructions, and submits it to the agent that lives in the compute instance that is running for me. So what is happening is on your qBraid account, you start an instance to get access to various quantum resources, and you could be building circuits yourself, but now there's an agent that lives in that instance, staying idle, waiting for you to give it instructions, and then it can start doing stuff for you once you provided instructions. So you can see it just goes ahead, submits a task. Next, now it's going to take like maybe 10 or 15 minutes for it to be running in the background and do this task. Meanwhile, what I want to show you is an enterprise-focused feature that we're also launching. One of the most requested things we've heard from the enterprise world is they want out-of-the-box working projects that they can just test out and build upon. And this is where we're releasing this Explore page. One of the cool projects that is inspired by our work with Airbus is this quantum reservoir computing. So let's just launch it in qBraid platform. And this is truly out-of-the-box experience where, okay, tiny hiccup. I'm going to have to find, there you go. All right, wasn't too bad. So I can just click run all, and the entire notebook runs. All the software that is going to be required gets automatically installed on your qBraid instance when you trigger, when you click that button. All you have to do is what I just did. So you'll see the right Python environment shows up automatically here. So this is QRC demo. And for those of you who don't know QRC, this is a very cool classical machine learning technique where you use a high-dimensional reservoir and avoid the deep neural networks. And all you're doing is this training this last output layer, which means training is much more efficient. So here in this notebook, what we're doing is we're using a classical reservoir and then a quantum reservoir, and then a combination of classical and quantum reservoir, comparing all of them, comparing how they each perform, and then do a whole bunch of analysis later. And so it doesn't just stop here. If you are building some of that yourself, what you can do is actually take this and deploy your project, one on Explore page, or you can also take this and deploy it as an API endpoint for the rest of the qBraid users to easily use. And what is really cool is as you deploy your applications, this becomes even available, to qBraid Claude, which is a qBraid aware version of Claude code. And you can just ask it, hey, can you explore QRC for NYC weather data? And what you'll see is it starts getting me the data, and it finds the QRC endpoint that we had deployed, and it can use that API endpoint for QRC to do work for me. So you can see it already finds the qBraid pod, and it is trying to download the data. And so it takes a couple of minutes, so I'm going to skip it for now, but I want to move on to the next part, which is an introduction to qBraid OS. So if you are a quantum computing company or a data center or an HPC facility, we will work with you to integrate qBraid OS for your compute resources. Once qBraid OS is up and running, this is the interface from which you will control all the access to various quantum computers, and you'll track all the jobs which are coming in. So here is where you can control all the providers. This is where you do device management. What I want to show you how easy it is for you to add a new device once qBraid OS is up and running. So a big shout out to Quantum Machines, who have worked with us to make one of their quantum computers at Israeli quantum computing facility available for this demo. So I just go ahead and add Quantum Machines, the QPU type. This is QPU, not a simulator. I go ahead, select gate-based. I can pick up on from any of these input types, or can define my own. So because this is Quantum Machines, the input's going to be Qua, their programming language. That quantum computer that we would be hooking up is superconducting. Number of qubits, 21. Continue. Price per minute, let's say $20. We do like very economical stuff at qBraid. And so once I hit submit request, the request goes out to the admin who's managing this organization. So they will approve it, or they can reject the request. So once they approve, the device goes online, and then any end user, based on whether this is private device or this is public. Let's say the device is made to be public, then any user can show up to qBraid, oops, and then they can program in any language of their choice and submit to this device through qBraid SDK. What is cool is, due to our integration with Quantum Machines, we're also able to open up access, pulse level access to these devices. So let me show you. For this device, you can see we now have a Quantum Machines provider that you can import. You just run the whole thing. And because there's so much data that Quantum Machines is exposing, you can get a whole bunch of information for various qubits, the device topology, and then submit various pulse level programs as well. So here, what we're going to be doing is we're actually doing a frequency sweep to find the driving frequency of the qubit. You can see it goes through. We can submit the program through the qBraid SDK and then get the result, plot various graphs, analyzing it. So this is going to keep running, and hopefully it gets me the results. Yep. So you can see the peak magnitude at 11 megahertz. So this is going to be available for many more people in the coming months. All of the tools that I'm showing, these are going to be rolled out through 2026, and we're actively looking for many more partners to try these resources. Now, I want to close out my talk by showing you and giving you a glimpse of what we mean by meeting you where you're at. A lot of existing quantum developers like to develop locally. So there, what is going to happen is you can just install various extensions and install qBraid SDK, qBraid CLI to get access to all the tools locally. That means you have the Python environment manager in your local VS Code, but then you can also get access to all the Python environments that I showed you on cloud through here. So you can access the kernels directly. So, or you can also manage your compute resources, start and stop the machines from here, and we'll be rolling out SSH features. So that means you start a machine from your local VS Code, and you can straight up SSH into that machine from your IDE. Then you can submit to any of the machines through qBraid SDK. Here, big shout out to another one of our partners, two of our partners, one IQM, and then another one, Quantum Rings. All of their simulator and devices will be available through qBraid SDK as well. So essentially a single API system, a single credit system, whether you want to do local programming or on the cloud, it's all made very easy. And then last, one of the coolest features is the integration with your own personal AIs that you already use on your desktop. So here you can see this is my Claude desktop app. I can go here and say, what tools do you have available? And there you go. So now we also integrate directly with all the AI apps on your desktop computer, which means, and these are given more or less the same access to the qBraid tools, which means I can just go here and ask, can you check the status of quantum jobs that I submitted in the past hour? Once again, it's going to take your permission and get all the information to give you the information that you're looking for. So it's the IonQ job is still initializing. Garnet, it seemed like it failed. Probably device is not available right now. It was offline. Rigetti Anka 3 is queued. And then let's do, how about the agentic task? Is it completed? If so, can you summarize how it did? And then it fetches the task that I submitted like maybe 10 minutes ago, and it's going to get all the information from the agent. So it found the task, build and run 5-qubit noisy quantum volume circuit. And let's see if it worked or crashed or something. Perfect. So it seems like task completed. It did all the work that we asked it to do. It installed the proper Python environments from qBraid. Qiskit was 1.35 times faster. That's what it found. And then you have, yeah, it basically did full analysis of the comparison between the simulators from two different providers. And with that, thank you so much for coming in. Thank you for listening to my talk and going through my demo. We've got so many different talks planned out for the rest of the event. So I'm glad, I hope you have fun. Thank you.
Really cool stuff. Our engineering team's been working really hard on all these advancements. Brand new UI, agentic tools, some really cool new integrations. So very, very proud of our team. You guys crushed it. We have next some enterprise use case talks from IonQ, IBM, Rigetti, Quantum Rings, Q-Control, excuse me, Unitary Foundation at 2:05. So we're having a 7-minute break now for coffee and refreshments just outside the door, but we'll see you here shortly at 2:05. Thank you.
relations. Also head up a number of our BD initiatives. Can everyone hear me? It's fine. It's a pleasure to talk about Xanadu's software stack and how we're pushing the envelope in photonic quantum computing. So for those who don't know Xanadu, we are a full-stack quantum computing company headquartered in Toronto in Canada, founded in 2016. Company's grown very quickly over the past several years, now has over 260 employees, mostly at our headquarters in Toronto, but I've got about 20 employees here in the United States and several others around the world. So Xanadu, like many of the companies they'll be presenting today, is developing a full stack. So what that means is we are not only building the photonic hardware, but we are also developing quantum computing applications and developing quantum software. And the idea is that we want to be able to connect all of those various pieces in a seamless way. Today, given the focus of this event, I'm going to be talking a little about Penny Lane, which is Xanadu's open source quantum software stack. And one of the defining features of that stack is that because we are a full stack, we can really optimize all the way down from the algorithms development down to the hardware itself. So just to give a little snapshot of the kinds of industry collaborations that we are doing at Xanadu, I thought it'd be helpful to highlight one of our flagship projects over the last several years with Riverlane and Rolls-Royce. Turn this. So this has been going on for about 2 years now and funded jointly by the Canadian government and the UK government. And the goal is to develop quantum computing applications that enable airflow simulations relevant to jet engines. And generally this field, which is computational fluid dynamics, or CFD, is really a promising area for quantum computing. And it's a place where we and Rolls-Royce and our several other partners believe quantum computing holds the promise to really change the nature of simulations in this field. So one of the challenges of CFD is that you really need to make sure that the problem can be written down as a program that can be submitted to a quantum computer. And this is really challenging because it's classically very hard to do and also very challenging to do to translate that into a format that a quantum computer can run. And so Rolls-Royce really brings that industrial expertise. This is something that they really wanted to remove the bottleneck. And so with Riverlane, we took Xanadu's Penny Lane programming library and our Catalyst compiler to really try to reduce the compilation time required and to reduce the key classical preprocessing runtimes. And we were able to do that successfully from by 1,000-fold, and to reduce the classical preprocessing from weeks to less than an hour. And this is really a major accomplishment, and it really happened because we were able to collaborate with leading industry players to do this. So a little bit about Penny Lane. It's something that is designed for industry impact. But what is it, and what about our other users? So Penny Lane is one of the most popular and well-maintained open source quantum software stacks today. We've released 43 versions to date, and we've got an active community on our discussion forum. And Penny Lane has something that's has a proven track record. We've hosted a number of quantum hackathons with over 10,000 participants. We've got 180 demos using Penny Lane. We have 60 of those that are based on actual published academic papers. And there are over 100 universities worldwide that are using Penny Lane to teach their students how to program quantum computers. So it's really a mature platform that has proven track record of results. And it really is an ecosystem. It's not just a single piece of software. And it's really popular because it's really well maintained, and there's a incredible depth of resources after close to 10 years of development. It begins with a user-friendly Python interface where the programming is done. It's equipped with, as I mentioned, Catalyst compiler for compiling and optimizing the programs, and a suite of Lightning simulators for executing those programs. And these can really be used with a number of APIs and other hardware providers and with the largest supercomputing centers globally. So we have plugins, as I said, that really are designed to make this seamless and easy. And I will say also, it's really designed for all spectrum of users, from the most sophisticated to those just learning. And just highlighting some of the educational resources and support that we provide. We have, as I mentioned, 180 demos, which shows how PennyLane can be used in papers for prototyping interesting applications. And it really is a way to loop you into the latest and greatest in quantum computing. We also have a robust set of quantum databases for giving examples of quantum data that can be directly loaded into your PennyLane programs. And then we have a compilation hub that highlights the exciting work that's picking up pace in the field here. And I'll say for folks who are really trying to get some validation that they know what they're doing in quantum programming, you can also complete an online training and coding challenge, a set of coding challenges where you can get certified and get badges and things to show that you really know how this all works. Now, because these demos are really one of the most attractive things about PennyLane, we want to show off this collaboration with the organizers here. We have made some of these PennyLane coded demos available on qBraid. So if you go to PennyLane, you can click directly and it will run a program on qBraid's platform. So this is something that we are proud of, that we are able to collaborate with so many partners, and qBraid's really one of those key ones. Now, moving on to enabling research more broadly, we realize there are many more research out there that might not be fully up to speed with using PennyLane in their work. But to help broaden this, we've worked with Oak Ridge National Lab through the Oak Ridge Leadership Computing Facility, which, as many of you know, hosts the largest, one of the largest supercomputers in the world, the Frontier system. And we were able to unlock research access to PennyLane and provide a parallel computing feature through one of our Lightning simulators called Lightning Cocos. And once that feature was unlocked, we had our team work together with Oak Ridge to onboard the Frontier users through a PennyLane and high performance computing workshop. So, we really want to make folks across the supercomputing community familiar with the tools that we've built and to make sure that they can use them effectively. Finally, I'll highlight one more collaboration that we're really proud of, which is the partnership with Unitary Foundation, who I understand we'll be speaking later, and Quantinuum. We've got this is really an area where we put together a software collaboration, which is kind of jokingly called Jeff Bridges, because it's bridging compilation. And the goal is to bring together different software implementations to make a common interchange format for compilation. We really want to be able to make compilation easier for end users, and one way to do that is to really bring all the compilation resources into one place and make them able to work together. So that's really the goal. For folks who are interested in getting involved, we always welcome additional contributions to PennyLane. It is an open source, user-driven platform. So you can visit pennylane.ai, check out our GitHub page. And if you want to show off your research or get custom built tools, you really should reach out and let us know what you're trying to build, and we're here to help. So thank you so much.
Thank you, Jonah. So, if any of you had traveled through O'Hare Airport on your way here and stopped in Terminal 1, you may have seen IBM System 1 chandelier right there and present. It's very, very cool. So, next up, and we're really, really thankful for IBM's support of the National Quantum Algorithm Center here in Chicago as well. So, next up, we do have IBM bringing up product manager, Sanket Panda. Thank you, Sanket.
All right. Hello, everyone. So, I know this is a developer event, so I want to start off by asking a quick question. Right in Python. Awesome. All right. So, keep your hand up. How many of you guys have used Qiskit in the past? Okay. Perfect. Well, I'm really glad to hear that because I'm really excited to be talking about how do we get to quantum advantage. We'll walk through a little bit of the IBM quantum roadmap together, and since a lot of you are familiar with Qiskit, a lot of you guys have probably run stuff on our systems, a lot of this might seem familiar, as well as some of the things that we have cooking over the next few years. So this talk will predominantly focus on the software tools required to reach advantage, but before we talk about advantage, I kind of want to talk about why we are here. So back in 2023, we had a paper that came out that's called the Evidence of Utility Before Fault Tolerance. Now, in this paper, really quickly, we had calculated accurate expectation values for a 127 qubit circuit, and it's something that a brute force classical computer could not do. It really meant two things for us. One, we reached a point where classical computers can't really simulate what a quantum computer is doing. And two, that meant that quantum computers are these useful tools for scientific discovery. After really having that moment and realization, we were like, oh, let's open it up for everybody else. So our entire fleet got upgraded to 100 plus qubits, and I think a lot of you have been really kicking the tires on those and been doing really, really cool things. Now that we have this really useful scientific tool, it's really time to put it to work. So one of the things that we believe will happen by the end of next year is reaching quantum advantage. Now, what this really means is we are performing an information processing task faster, more cost efficiently, or more accurately than a classical computer would be able to do alone. And to really do that, it needs to be something that is verifiable and classically efficient. So we need to be able to do that together as a community. And for us, it means that we are building up the tools and the hardware to enable you guys to also come on this journey and discover advantage with us. So we spent a lot of time since that moment really thinking about what are the tools that really unlock you guys to come up with quantum advantage as well. This is a collection of hardware and software tools, as well as other cool, neat power tools to help you build algorithms and apply them to applications. I know it's a lot, and we will go through each step by step. Now, at the heart of all of this, it's a quantum computing tool, right? Qiskit runtime. These are the capabilities required to run a quantum workload accurately and efficiently. We start there because, that is the core element that we start off with in the utility paper, and critically, the main thing you guys are going to be foundationally using. It's changed a lot. When we first introduced Qiskit runtime back in 2022, we had these runtime primitives for collecting samples as well as accurate expectation value generation. Now, since then, when we did that, we had a tremendous speed up. Over time, what we really balance as a developer, what are the right amounts of controls you guys need, as well as how do we make sure you guys are doing things quickly, cost efficiently, and also, accurately. So over this time period, we expanded those primitives with new tools, such as parameterized compilation. These brought quite a bit of speed if you're doing things like you have a circuit and you need to compile it once and you want to do a parameter sweep. They're fairly quick rather than spending a lot of time recompiling. As well as earlier this year, we had upgraded our stack to also feature utility scale dynamic circuits. These are tools that help you express more complex circuits, and you can do things like mid-circuit measurements, feed-forward, classical calculation, all within the runtime of a single circuit. To make these more scalable, to make these perform at a high quality, we introduced other capabilities in there, such as parallel if controls, stretch operations for dynamical decoupling, and soon some timing visualizations. Now, as I kind of mentioned, right, developers need control as well as performance. So in a couple of weeks' time, one of the things I'm really, really excited about is a new error mitigation, a primitive for custom error mitigation. We call it the executor, and it'll help you build up custom error mitigation methods with boxes, annotations, and layers for things that you might typically want for learning-based error mitigation. And I'm glad that the Unitary Foundation is here, so things like MITIC and others can leverage that type of capability. Now, we talked a bit about the quantum computation, but I think we all know here that when you want to run an algorithm, there's the quantum computation as well as the classical part of your workflow. You need a connective fabric to help you integrate both together into a seamless workflow for running, solving a problem. So back in 2023, we started off with Qiskit serverless in the cloud. It was a tool that helped us, get whatever CPUs, GPUs that you might need for persistence, for distributed transpilation, for anything else for post-processing. And we have that on the IBM Quantum platform. Last year, we worked with RPI and put the Slurm plugin with their Amos supercomputer and had all of those quantum and classical resources managed by that single resource manager. But as we dove into that collaboration and we worked more with HPC, we realized one really core popular feedback that we kept getting over the years, and it was the most popular feedback last year at the Quantum Developer Conference. Please, 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 can we have a C API? So we set about doing exactly just that. Now, similar to Penny Lane, we started off with a Python API because that is a pretty neat and approachable tool. But we've seen over the years that our users want performance as well as want the ability to have other languages that they're familiar with and comfortable with. So when Qiskit 1.0 came out, we've been replacing a lot of its internals with Rust, making it more performant, making it faster. And then with Qiskit 2, I'm really, really happy to say that there's a standalone Rust crate for C foreign function interfaces. What that really means is two real things. One, if you want to build your own language bindings, you can. So that could be to things like C, sure, C++, as well as people here who want to write in Julia. That's pretty much really simple, and you're not sacrificing performance for it. The second thing is that you have an end-to-end demonstration with C, right? High performance and something that you might want to use things like OpenMP, MPI, if you're running these high-performance computing workflows. But, as we kind of move forward with these high-performance workflows, you'll see us over the next few years introducing some new tools, things that help you profile and analyze what's happening across each of these quantum and classical resources, as well as other workflow accelerators to help you optimize advantage scale workloads instead. We've talked about the underlying compute. We've talked about how to manage it. Now, let's talk about how to discover new algorithms. So to really help at least introduce that, right, I want to talk about this framework, right? This is what we call a Qiskit pattern. We introduced it in 2023 to really break down what are different tools really doing and what you might expect from each. So when we talk about these, there's really 4 steps, right? You have the mapping your interesting problem to quantum circuits and observables, optimizing that for execution, actually running it on a quantum computer, and then post-processing the result. Simple enough, right? And the Qiskit SDK really gives you the base set of tools you might need for high-performance research across these things. Now you can actually do that with C. But when we talk about what do you need to actually discover new algorithms, we have spent a lot of time working with institutions like Riken, Cleveland Clinic, etc., Basque and come up with useful tools across this workflow. I'll talk about one of them, but generally speaking, right, when we talk about research power tools, they need to be really two things, right? They need to be modular so that you can hot swap whatever you need for your custom research. And secondly, they need to be, well, performant, right? You're really pushing to the cutting edge, so the tools shouldn't really get in your way to do so. For example, one of these such things at the very end you might see is a post-processing tool called SQD, or sampling-based diagonalization. I really like this one really specifically because our partners and friends at Riken, home to Fugaku, one of the world's fastest supercomputers, had done a workflow where they were able to have a beyond exact diagonalization of iron sulfate clusters. Now, with that, you get to have these interesting chemistry workflows that we weren't necessarily able to do with just a classical computer alone or just a quantum computer alone. You need to really use both to do that. And since we did that initial research, we repackaged it as a software tool that's open source, like all of the Qiskit stack, and it became a tool that you saw others like Cleveland Clinic, Lockheed Martin build their own amazing research 5 times faster than just building it up from scratch every time. So, as we kind of progress in the next few weeks, I'm looking forward to seeing you guys there, but we're going to be doing some exciting new error mitigation work with HPC and these advanced classical mitigation tools. And moving forward into that regime, I mentioned you have to be mapping your problems, right, at the very beginning of it. When that sets the foundation for the rest of your computation. So making sure that you all have high performance mappers to actually set your rest of your algorithms is one of the things that we're really excited to do. Now, to make sure we have enough time, I'll make sure that the last bits are speed run a little bit. I know I've thrown a lot at you, and it seems like a lot of things. And that's kind of the point, right? There's these modular abstractions across the Qiskit ecosystem. Now, if you're a researcher that wants to dive into the nitty-gritty, things like the Qiskit SDK and the add-ons are exactly where you can configure every little knob that you might need, right? On the other hand, for enterprises who want to explore applications research, we have these neat tools called Qiskit functions, where we get to work with our partners to wrap several layers of that workflow and present it in a little bit more of a user-friendly way. These are still, I want to make sure that people understand, these are still research tools for application research where you have customized workflows for error mitigation, suppression, but also even things like mapping. So this comes in really 2 forms. The first is these circuit functions, right? So if you want to build up your own mapper for application research, and you don't want to think about quantum hardware performance management, things like learning transpilation, noise characterization, error mitigation, suppression, you can work with partners like Q-Control here to actually focus on just your circuits and observables, and then you get exactly the outputs you need to actually continue building out your mapping algorithm instead. Now, for those of you who are doing industrial research, such as logistics, optimization, molecular simulation, we have application modules instead, application functions instead. These abstract mapping as well. Mapping, as you all know, is an ongoing research challenge. These partners that we have in this space are doing the cutting edge to at least abstract the quantum circuit mapping so that you can focus on things like your higher order binary optimization problems, or for example, your molecular definition. So these circuit functions from KEDMA, algorithmic, and Q-Control give you these error mitigation, suppression, transpilation, give you scale right out of the box. So your mapping is what you focus on as you develop these algorithms. On the other hand, if you, like I mentioned before, if you care about application research, we have a host of partners who are doing tremendous work, like Q-Control, to do things in simulation, optimization, differential equations, as well as machine learning and finance. This is the cutting edge of research that is incredibly exciting for me. Now, as we progress on, I want to make sure that people get this last bit, where your applications are only as good as how much you measure it, how you measure it, right? Now, earlier this year, we worked with a host of organizations, some of whom are in the audience today, to build out an optimization benchmarking library to really know what are the problems that are of merit, where does classical computing really stop scaling, and where do we need to explore with quantum computing instead? And as we progress into next year, the thing that for us is really benchmarking use cases from beyond just optimization. So all of those application areas that you saw, having benchmarks for them to really know where quantum and classical need to work together to solve the world's most intractable problems. Now, I'll leave you guys with this. Qiskit is really the tool that we have been really excited about. It's a lot of that stack is open source because we believe that for research to really progress, you need to do so. Things like the Unitary Foundation has really told us quite repeatedly that this is the most popular software development kit amongst developers, with a lot of contributors beyond just IBM. Those add-ons, those modular power tools are things that speed up research. And we see other enterprises, other academic institutions leveraging higher level abstractions to build up new custom algorithm and application research. So I really do hope that you guys join us in the next 2 weeks for the Quantum Developer Conference in Atlanta, as well as get started with Qiskit. It's open source, and give it a go. All right. Thanks all.
Thank you, Sanket. That was fantastic. Next up, we will hear from self-proclaimed professional storyteller, Vadim Karpysenko. Vadim currently serves as head of developer relations at IonQ and previously held roles as developer advocate at AWS and Microsoft Quantum. Please welcome Vadim.
Give me just a second. All right. Okay, start mirroring. And here we go. So I'm a typical developer, so I came without slides. I'm going to be presenting everything through the browser. I'm going to be talking about what I've been doing as a developer, as the head of DevRel, developer relations. I'm so sorry, I'm a little bit under the weather, so hold with me, please. So IonQ is the manufacturer of quantum computers. We're using a different modality of quantum or qubits. We trap ions, heavy ions, in the changing electromagnetic field and manipulate their state by, using lasers. So if you want to learn more about our company, I would recommend just to go to ionq.com and read more about it. And we've been working with a lot of companies in the past several years. qBraid is one of them. And actually, qBraid helped build us the platform for the whole hackathons, which I'm going to be talking about today. So I've been on a road for the past month. I've been to check. Okay, now it's working again. Here we go. So, in the past 4 weekends, I've been to Singapore, This one is working now. And this one working as well. What's happening? Okay, just in case. Okay, if this one is not going to be working, I have a backup option. Okay. So let me tell you what type of problems we're giving to students and professionals to play with so that they can experiment or kind of have a goal in mind and try to apply their knowledge, what they know from quantum. Not only quantum, we actually encourage them to use also classical knowledge or kind of classical algorithms. That was kind of the best solutions, for example, when we kind of create the challenge in partnership with Microsoft. So the challenge itself was just to try to come up with a business solution which is going to help you to kind of get the hydrogen from water. And we provided a lot of background information for the students. So the task was not just it wasn't completely open-ended. There was a task we had in mind. And there were about 100 participants in this hackathon. They spent more than 48 hours, I think it was close to 50, just trying to address that problem. And that was very interesting because we had not only physicists or computer science students in the group, but we also had people with MBAs, with business background, and they tried to focus not only on technical solution, but also on a business solution, how they can then come up or gonna get their technical ideas and apply business approach to them. So in a different hackathon, for example, this one was in Geneva, in CERN, in partnership with Moderna, we ask our participants to play around with the idea of messenger RNA folding. Why it is interesting problem to solve? Because depending how rigid the mRNA is, it will affect the protein folding. So it was interesting for students apply quantum here because there are so many different combinations, or sorry, give me 1 second. Yeah. So different nucleotides, they can connect in very different ways. So to go through all this combinatorics problem, that's where quantum can be applied. And students did an amazing job formulating the problem and then playing around with all those different conformations to get the solution, which can be, of course, right now solved classically, right? But as we go bigger, classical computers will simply spent years trying to solve this, where quantum can get the combination significantly faster. Another example of the challenge, this one was in Singapore just last weekend. It was counterparty credit risk. So we asked our participants just to predict what's going to be the price for the, I think in this case it was European options. So it's a financial problem. So you can see that we tried different type of challenges for our students, right? We tried financials, we tried biophysics, we tried other stuff. What we did, for example, in South Carolina, and that's probably going to be my last slide, that's the challenge we developed, which takes basically classical problem, instant insanity puzzle, and then you need to go through all the configurations of the cubes to figure out how to get the configuration where you will have 4 different colors on each side of those 4 cubes. It sounds kind of easy, but to formulate, to encode the state into the qubits, and then figure out what circuit should be, right? And then play around with variational QIOA, for example, right? Or Varkite, variational quantum imaginary time evolution algorithms. That's very interesting for students. And we used qBraid as a platform for the hackathon solutions. It actually helps students quite a bit because they don't need to set up environments. Sometimes it is so much easier for them just go into the cloud, right? Use qBraid, their environment, because everything is pre-installed there. We also collaborated with qBraid very heavily on MIT Hackathon, which actually happened this year as well at the end of January, if you don't know. And I actually invite you all to participate because there is in-person component, but there is also remote. And this year, I actually just confirmed with Ricky, we're going to be collaborating again on the challenge for MIT Hackathon. So please, you're all welcome to try it, right? And as you can see, qBraid actually developed quite a nice environment. And in this particular case, for the South Carolina hackathon, we restricted a little bit more, right? Previous hackathons I showed you, it's more kind of open-ended. We're just saying that you can play around with messenger RNA folding, right? But we don't give you exactly how you can do this. For South Carolina hackathon, or Quantathon version 2, it was, as I mentioned, this instant insanity puzzle. And interestingly enough, we thought that students might not like it, so it was kind of experiment. But from the feedback, NPS score for that hackathon was actually 80, which is amazing for events like this. So I think the trick was for the students not just simply gonna throw the problem to them, but also provide some additional information. That's what we've been doing, for example, with MIT IQ hackathons, and also tried with a South Carolina hackathon. So for them, there is a challenge, but we also provide the kind of similar solution, right? Or a kind of notebook which demonstrate how a particular problem can be solved. In this case, students who are not even familiar with the quantum, who just wants to make their hands dirty, they can come, play around with the code, solve something. If they don't know, for example, Qiskit, right? They can just follow the instructions and read more about it, learn more about it. So that format actually works very nicely. And as I mentioned, qBraid already built the whole platform for the hackathon. So if you're interested, stop by at our table, ask me about hackathons, right? Our experience, and use qBraid for their platform in general, because it helps students a lot. Thank you. For the technical difficulties.
Thank you so much, Vadim. It's been a pleasure to work together on these hackathons. Next up, we have a personal favorite for researchers on the qBraid Lab platform with Rigetti. And so please welcome Mike Peach, Head of Business Development at Rigetti. Mike previously served as General Manager of Red Hat's middleware business and brings that expertise to the quantum space. Thank you, Mike.
All right. Vadim, I think you jinxed it up here, man. All right, we did a check, and this worked before, so this is not what's supposed to happen. There we go. Great. All right. Thanks, everyone. I am Mike Peach, Vice President of Business Development at Rigetti. As you've seen earlier in the keynote, we are a partner of qBraid and very proud to be one of the hardware providers on qBraid's platform. So thanks, Tarni and Brian and the qBraid team here. So we're very excited to continue working together on the great stuff that we've seen examples of already. So Rigetti is a quantum computer maker, so we're mainly about hardware. We have our own fabrication facility. We make superconducting qubit chips. We make the full stack, the full system based on those chips, including the operating environment and the lower levels of software. In general, applications aren't our day job. However, as we'll see in a little bit, we do have application teams in several areas that generally collaborate with industry and academic partners on various kind of research projects, partly just as a general contribution to developing quantum computing technology, and certainly, somewhat selfishly as an internal resource that generates requirements and helps us focus on what to optimize for in our building of quantum systems. Our flagship system today is 84 qubits at 99.0% CZ fidelity. By the end of this year, we'll have more than 100 qubits at 99.5% CZ gate fidelity. So to just calibrate you a little bit on where we're at in terms of our development, we have about 150 people. We're headquartered in Berkeley, California. Our fab is in Fremont. We have several facilities around the world, including a fairly sizable application software team in the UK. So, like many of the players out there, we think of the application space for quantum computing, the areas where quantum is likely to bring significant advantage, in three main areas: chemistry simulation, optimization, and machine learning. And for basically historical reasons, no particular design choice, we don't really have any expertise on the chemistry side. However, we do have some pretty deep expertise on both optimization and machine learning. And so what I hope to share in the next few minutes is a couple of examples of some of the work that we're doing there ourselves, and importantly, in collaboration with industry and academic partners. So I'm going to focus on a particular approach to how quantum can help computation in general. So, one coming into the field may think, okay, a quantum computer runs quantum algorithms, give me a quantum computer, I'm going to put a bunch of software on it and it's going to do interesting things. Once any of us kind of gets into it a bit, we pretty quickly understand that most applications of quantum are going to be very hybrid in nature and involve lots of back and forth, lots of interaction with classical compute. And one particular approach in which quantum computation can enhance a general problem area, a general problem space, is to transform the starting data that's going into a problem, transform that data quantumly, and then feed that quantumly transformed data into the remainder of what would be the traditional classical pipeline. In the straightforward classical pipeline, sometimes you start with just classical data in its raw form. In many cases, you do have to do some kind of transformation of that classical data, whether it's tokenization, whether it's some kind of quantization, etc. And in some cases, the quantum transform replaces that step. In some cases, it is kind of an adjunct to that step. So let's look at that in the example of quantum machine learning. So in a classical pipeline, we take the raw data, we transform that into the data that trains the model using a feature map. And then once we have a trained model, we use that at runtime in production to run inferences. An approach in which quantum can enhance that pipeline is to quantumly transform the classical data and use that quantum transformed data to do the model training. And there are a couple of different ways to do that. There are quantum neural networks, there's the quantum reservoir approach, we heard a reference to that earlier today. There are support vector machine approaches. In general, the idea is a transformation to a higher dimensional space often nonlinear, and a transformation that enables something to happen more easily, more efficiently. There are key questions, though, is that it's not always relevant, it's not always useful, it's not always helpful. So this is an important lens with which to look at any of the research going on in this area. And to try to help with a little bit of intuition about that notion of transforming data into a higher dimensional space to make something a little more interesting, here's kind of a classic picture from the classical world on support vector machines and kernel methods. If I have a set of two-dimensional data as I do on the left, there's no easy way to linearly separate the two different classes of data that I'm trying to find. However, if I transform that data, in this case it's a very simple transformation where I have x, y, and I now generate x squared plus y squared as a third dimension to that data, I end up with a paraboloid that I can then slice horizontally with a hyperplane, and I now have that data cleanly separated. It's not exactly that way for all the kinds of transformations I'm talking about, but hopefully that motivates a little bit of an intuition about how to think about what these transformations do. So one specific example of how we're employing this kind of transformation in machine learning is some work with Moody's and Imperial College London. And what we have been working on with them, and this work continues on, is using economic data to predict recessions. And this particular work is really interesting because it also involves some new developments on the classical side, namely signatures and signature kernels. There's a reference up there if you want to snap a photo and dig more into that. It's very interesting work where you transform the data. There are two steps of transformation. There's a quantum transformation, and then there's transformation into this space of signatures. And with some of the preliminary work that we've done on that, we compared to a classical baseline of probit, which is essentially a regression that uses 8 economic variables, things like GDP, consumer price index, yield curve, et cetera, and you're predicting a binary dependent variable. So in this case, to simplify the problem and come up with a useful example, we have these 8 economic variables. We're trying to predict a recession 12 months from the moment of evaluating those inputs. So train a model using historical data and then compare the results. We have the probit baseline, and then using pure classical signature kernel methods, we get some level of improvement over that probit baseline. But then further quantum transforming prior to the signature kernel step, we improved even more. So separation, that is a measure of how well the prediction goes. Do I predict positive in the 2/3 and above probability cases where the actual data says there will be a recession, and similarly on the negative side, do we correctly predict in the cases where the prediction was less than 1/3, 33%? Just another way of viewing that same data and how the combination of signature kernels and quantum did better. On the left is the classical signature, on the right is the quantum. What we're looking for is for the red line, which is the prediction line, to follow the actual line, the actual data, which is the green. And you can get a little bit of a visual sense of how in the quantum enhanced version on the right, that red line prediction is following the green line much more accurately. So this same idea, actually, we're stepping back up away from machine learning specifically, this general notion of quantum transformation is also relevant in the area of optimization. So if we take a classic optimization workflow, we have classical data, we may do some pre-processing of the data classically, we feed that into a solver, that comes out with our optimization result, finding as close to the ideal minimum or maximum as possible. Turns out that by preconditioning data in this idea of quantum preconditioning and feeding that quantumly transform data into a solver, we can get some very good results as well. So we've been doing some experimentation. Again, this is a combination. In this case, this is mostly Rigetti's internal folks. We have done sub-collaborations with academia on this. The paper's noted up there as well for anybody who wants to snap a photo and dig into this a little more deeply. But what we've been doing is trying this quantum preconditioning against and feeding it into different optimization algorithms such as simulated annealing, Borer-Montero. And in those two cases so far, we haven't found super impressive speedups. But when feeding quantum preconditioned data into the Gurobi optimization solver, we found on the order of 10x improvements in accuracy and speed. And we actually used that approach on a specific data set in the context of energy grid optimization. There's a fairly well-known data set that's available from ARPA-E that characterizes the energy grid of the state of South Carolina. And we applied some of this work that we've been doing on there. Using that data set and trying to put this optimization approach into the context of a real world problem. So I'll end with a tantalizing idea. So there's this concept that's always fun to talk about, especially to more newbie audiences in quantum, namely magic. So as you in the know are aware, so quantum circuits with magic are ones that are outside the Clifford gate set. So that actually allows you to achieve universal quantum computation, right? So you get outside the being locked into the 6 points that the Clifford gate set gives you, and this gives you essentially, the opportunity to play with the entire two-dimensional space of a qubit, the entire Hilbert space there, and a conjecture, not fully proven or understood, is that using more magic, so using more, let's say, T gates, the pi over 8 gate that, again, gets you access to the bigger, the full swath of the Bloch sphere of a qubit, does actually enhance some of these algorithms. So we've done some exploration, particularly, now this data on the screen here goes back to the quantum machine learning example from earlier. We found that that in some of the harder problems with less training data, adding more magic, more T gates to the transformation circuit set significantly improved the output. And so a sort of a more specific conjecture that's starting to form out of that, and which again are machine learning experts. Most of these guys are based out of the London office. Is that the typical trade-off between generalization and approximation? This notion of if I try too hard and make it overfit and make too specific a circuit really compromises my generalization and vice versa. But if I add more magic, it actually pushes out that whole boundary and lets me have sort of more of my cake and eat more of it too, if you will. So that's ongoing research actively pursued today, also, again, including some folks at Imperial College London and some financial institutions such as Standard Chartered Bank. We don't have a paper yet published on this, but stay tuned on that. Very fascinating results coming out of that team of folks. So I'll end with the positive note. There's really interesting work that's being done today in the area of quantum algorithms. In our case, some of the results that I've shown have been largely in simulation, but since we're a hardware company, we always also run it, in some cases, a subset or a smaller scaled version of the problem on our actual hardware so that we can really track how the noise and other challenges of real world hardware are impacting the viability of these different approaches. But the hardware's getting there, the software's getting there. We can't wait. We're soaking up as much error mitigation and error correction as we can to help the situation here. And so anybody who's inspired and interested in this kind of stuff, we'd love to talk to you and help you help us and help lift the rising tide that's bringing all the boats in the quantum world up at the same time. So with that, thank you very much.
And next up, we have a fellow UChicago Duality Accelerator organization. Quantum Rings develops powerful quantum simulators, scaling to hundreds of logical qubits, reducing wait times, and doing so cost effectively. Please welcome Bob Wald of Quantum Rings.
Yeah, thanks for that. We'll see if the digital gods are with us. All right. Yeah, it's delightful to see everybody having problems with AV because everybody's always asking us when quantum's going to be ready. They should ask when AV is going to work. All right. So I saw from the hand raises earlier that there were a lot of developers in the room, a lot of people that play with Python. Real quickly, how many people in the room are bullish about quantum right now? Show of hands. How many are skeptical? Be honest. All right. So there were at least 5 people brave enough to raise their hands, which I think probably means you guys know what you're talking about. Today, I'm going to spend just a minute talking about the state of quantum from my perspective, putting a couple big pieces together. Then I'll tell you a little bit about what Quantum Rings does. We'll go deep into a little bit of geekiness in terms of the 2019 Google Quantum Supremacy Experiment and how we've continued that work. And then I'll share something cool about this new thing that we're calling Open Quantum, which is going to give more people access to quantum compute. So the state of quantum. If you are one of the bulls, the quantum bulls, you're going to say that by the time my children or my grandchildren are around, we're going to have cured cancer, electronic cars are going to go forever, supply chains will be perfectly optimized, we'll solve world hunger, portfolios will be worth 10x what they're worth today because we will have optimized. You're going to say that quantum computing holds the promise to transform the world, and we're going to unlock trillions of dollars in the next couple years. And actually, I happen to be one of those people too. If you're a bear, you're probably looking at this and you're saying, well, I have to wait like hours or days. They're super hard to access. They're super noisy. We can't get the error rates low enough. They're super expensive. If I try to do VQE on these things, it's going to cost $1 billion to do something. Frankly, they just don't work. And we don't even know if those algorithms are going to have exponential advantage. Those guys are also right, and I happen to be one of those also. And I like to look at this DARPA chart to sort of like start to explain maybe some of the gaps there. So DARPA put this chart together. It basically shows on the bottom axis the number of computational qubits, logical qubits, that will be required for a number of applications that they're studying. On the vertical axis, it's the number of operations that are going to have to take place, and they've scatter plotted those out. And when they published this in September of 2024, we had 0 real logical qubits. A couple of companies would say they would have demonstrated them at that point, but you couldn't run on a logical qubit at the time. Quantinuum just announced that this year they're going to have 50 logical qubits. Atom Computing shipped a system, I believe, earlier this year saying that it had 50 logical qubits. And so if you look at that, that means that we're here now already, right? We're right on the cusp of incredibly useful, computationally super hard problems. And IonQ, thank you for presenting earlier. If you're to believe the IonQ roadmap, we'll have 800 logical qubits in calendar year 27, and we'll have 8,000 in 29, which means that we're really getting into the heart of all of these really hard quantum problems in the really near future. By the way, that red diamond up there, that's RSA 2048. So I hope you all have your post-quantum cryptography strategies well in play. But on top of that, the more innovators are coming into this space, the more we're pushing those algorithms down. They're using less operations. They're using fewer qubits. And so at the same time that the quantum computers are becoming more capable, the algorithms are requiring less. And it is an exciting time to be both a bear and a bull in quantum. All right, so quantum rings, what do? Quantum Rings is on a mission to democratize quantum computing. We're trying to bring more people into the ecosystem, get them playing in quantum quicker. When people enter into the ecosystem, they really quickly figure out that if you're going to write quantum software, you either need to run on these simulators that require exponentially increasing amount of compute and CPU, or you have to run on quantum hardware, which have such high error rates that you pretty quickly fall apart. So we founded the company asking, what if we could just build a simulator that scaled a little bit better? Well, we did, and we let you run hundreds of qubits with millions of operations with a relatively high fidelity, which you can tune on your desktop or in your cloud. Now, I'll put some user numbers up there saying that in the few short years that we've been around, we've amassed a couple thousand users. We've seen about 8 million circuits executed, users from 250 universities around the world. And we've been a partner with qBraid since 2023. Qiskit was just up here, so I want to say we're fully Qiskit compatible. So you can, when you hit the limits, you can always add quantum rings in. In fact, if you go to their website and you grab the 127 qubit optimization problem that they show you, which allows you to exercise the quantum compute capability, it takes 8 minutes on a real quantum computer, costing you about $800. You can run it in 30 minutes on a laptop using the Quantum Rings SDK and actually get a more accurate result than the example output on the documentation. But what I really want to geek out on is Google's 2019 quantum supremacy experiment, which was supposed to take 10,000 years for the fastest supercomputer, and we're going to talk about that. All right, so quantum supremacy, what is that? We actually don't say quantum supremacy too much anymore. We talk about quantum advantage. But if you think of the universe of problems that are solvable by classical computers and the universe of problems solvable by quantum computers, that's quantum supremacy. Now, in 2019, Google claimed to have achieved it. Now, that was a very controversial claim. There have been a number of additional claims since, but they did it with this thing called random circuit sampling. So random circuit sampling works by essentially, I'm going to oversimplify it. The quantum geeks in the room will tell me I said this terribly, but we generate a random circuit with a specified amount of complexity. We then have to sample it millions of times, and then we make sure that the results matched the constraints that were encoded in the circuit. It's not particularly commercially useful, but it's computationally very hard to do, which makes it a nice kind of benchmark problem to try to see if we got a quantum computer right. Google even acknowledges not commercially useful, classically intractable. Why is it such a good benchmark then? Well, it was high profile because they were the first guys to claim quantum supremacy. They published all of the QASM files, so you can just take them and run them, all of the output files, all of their timing data, and they provided a metric called the linear cross-entropy benchmark, which lets you quantitatively measure how well you did versus them. And so we did do that experiment with our simulator, and we published a paper at the end of last year with Arizona State University and UIUC's NCSA, showing that you could run that experiment on a CPU-only node with 32 gigabytes of memory with the Quantum Rings simulator. And that the distribution of the samples looked exactly like it should. And in fact, when you run the linear cross-entropy benchmark, where up is better and down is worse, the red line was the Quantum Rings result versus the blue being the Google. Now, by the way, you should expect Google's result to be really low because they're really running it on a quantum computer, which means they have physics to deal with, right? Which is much cooler than running it in software. And so you can check that out. By the way, I'm going to start putting a QR code. It'll be on for a few slides if you want to try quantum rings. But we have the full paper up. You can also download the source code to replicate the experiment yourself. After we published that paper, though, this is where the interesting part came out, and this has not been published yet. So NVIDIA reached out and said, well, what about if you had a GPU? And so we found that if you split the problem into two different steps, first, calculating the quantum state, which is the really mathematically intense part, and then taking all of the shots, we could get about a 40x improvement on calculating the quantum state, which meant that that only took about 12.5 minutes. Now we had to run on a research computing cluster to do that, so we had a whole bunch of CPU nodes that were being completely unutilized. And so we said, hey, what if instead of running 2.5 million shots on one CPU, we distributed that quantum state and we took 25,000 shots on 100 different CPU nodes. And it worked wonderfully, and the total experiment finished in 1 hour and 15 minutes, which meant that now you're getting essentially a 7 times 10 to the 7th speed up over the estimate of 10,000 years. And it's only 22 times slower than a QPU. The other crazy thing is that if you want to actually ramp that up and distribute it across more nodes, it actually scales linearly. And so as you go up to, say, 1,000 instances, you actually can run the entire experiment in 17 minutes, which is only 5 times slower than a quantum computer. Now, I'm not saying that quantum computers don't have a place. Like, classical compute is not going to scale the way that quantum computers are going to scale. But what I am going to say is that there's a lot of opportunity to do things that we're waiting on quantum computers for by using a quantum approach with HPC simulation today. And there's nothing about this that's limited to RCS. You can do RCS. You can run peaked circuits, VQE, Shors, HHL, QML. Basically, any of the well-known quantum algorithms, if you just give us a chasm, we simulate it. And so the hope is that we're sort of shifting this line. And if random circuit sampling is in here, then the question might be, what other problems that you guys are working on are also in here? Okay, so that was the geeky part. Now I'm going to move on to a second thing. So I said we traditionally have been in the business of large-scale simulation. But what we really want to do is make quantum computing accessible to as many people as possible. And so open quantum compute, we actually asked the question of how might we make access to quantum compute ubiquitous? Like, how can we remove as many barriers as possible to get as many people running on actual quantum computers? And we found a partner in the AI space running on a framework called BitTensor, which is a decentralized incentivization network that allows for funding of AI projects. And we actually found a way to get a substantial amount of resource to buy quantum computer time to give it away. And so Open Quantum is going to let people execute workloads on real QPUs. Today, we have Rigetti, IonQ, and IQM, but we'll have more coming soon. These are gate-based quantum circuits taking QASM2 or QASM3, and it's free for basic circuit execution. And so each month, hundreds of thousands of dollars of QPU time will be purchased and given away. Sounds kind of too good to be true. And so how could it possibly be free? Well, as a part of this, what we're trading is the data, right? And so what we're trying to do is actually build a comprehensive data set that says, what are all of the quantum people doing, right? Are there regional clusters that are working on certain types of problems? Are students working on different things than professionals? Are people from AI starting to explore ML? Or is that still just something we're talking about on stages, right? Citations will be required. So if you do use Open Quantum, you have to cite it in your publications. And there will be limitations in place just in terms of number of shots and throttling while supplies last. And so, yeah, if you guys are interested, it is in private beta right now. And so you can sign up. We do have users running quantum circuits today, and we'll be onboarding more and more users that are on the wait list as we go. Thank you all for your time today.
Thank you, Bob and Quantum Rings. Next up, we have the Unitary Foundation welcoming lead developer Jordan Sullivan. Please.
Ooh, clicker works. Oh, that is the wrong mic. Okay, hi everybody. I'm Jordan Sullivan. I work at Unitary Foundation. I lead our open source compiler collection development, and today I'm going to tell you a little bit about what Unitary Foundation actually does and a couple of our projects which make use of qBraid. And at the end, I will share how you can get involved yourself. So first, how many people know what Unitary Foundation is? Okay, that's pretty solid, pretty solid. Okay. So we do three main things. First one is our microgrant program. This is kind of the flagship Unitary Foundation program. There's $4,000 of no strings attached money for quantum open source projects. Next, we have our own research and development teams. We call this Unitary Labs, and that is where we do our work on compilation, benchmarking, quantum error mitigation, things like that. And finally, we have a very, very active community of over 5,000 quantum tech developers on Discord and GitHub, like certainly over 100 different GitHub repos, and people who work on such projects are represented there. Jobs board, weekly Discord hours, etc., etc. This is our team right here. It's pretty small. It's quite distributed about the globe. We have folks in the US and in Europe, and we all work on different aspects of the program. Okay, so I will just briefly run through kind of like by the numbers, what do these microgrants do? What are we talking about here? So we've funded work that has resulted in like more than 400 different papers and 40 new libraries, lots and lots of contributors and maintainers. 3 people have founded startups from literally $4,000 of microgrant money and gone on to do much, much bigger things, as well as an education nonprofit. So just a handful of topics that have been past areas of interest for awarded microgrants across hardware and control, compilation, algorithms, quantum error mitigation, all sorts of things like that. But we also do other grants that are more cross-cutting, say education-focused, stuff like that. Okay, so Unitary Foundation Labs, this is our R&D stuff. So at the moment, we have 2 main focuses. So on the one hand, we have benchmarking, and secondly, compilation. Okay. So first, I'm going to talk about benchmarking here. This is a screenshot from Metric. Has anybody heard of Metric? Okay, yeah, very solid. This is a very Unitary Foundation friendly room. Thank you. So Metric is a quantum benchmarking web API. So we have over 600 benchmark results from 750 different papers. So basically, you know, we constantly have these papers coming out claiming that they've gotten specific results, giving resource estimations for what is required to run a particular application. And so the idea is just pull all this data together, and this is really part of Unitary Foundation's mission, like try to do things that are useful for the whole community, help eliminate the need for duplicated effort and make it easier to understand where the field is at. So that is the sort of, okay, let's just take in the existing papers and report them. But okay, well, maybe a lot of those are like really special tuned, you know, you have like really, really close pulse level access to your hardware. Maybe that's not super realistic for like a normal person who's gonna run through like Amazon Bracket or something. So we also have actual hardware benchmark tasks that we run as like a neutral third party. So this is what we call Metric Gym, and this is where we use qBraid, where we use it to access different quantum backends. So this is just a little architecture diagram of Metric Gym. It has this front-end CLI, different cloud runners. There is a set of verifications and exporters that actually interface with the metric.info website. And then when we go to actually run applications on quantum devices, we go through the qBraid SDK. So huzzah for that. I'm very excited about all of these new agentic AI features where you can just be like, hey, run me a bell circuit on Rigetti and IonQ. Like we're constantly saying that like in words, but then being able to actually do that is like, it takes so much time to be like, okay, like how do I translate? Like you're scrolling through documentation. So I'm excited about that. Okay. So our second area in Unitary Foundation Labs is compilation. So we have a much longer running project called Mythic, which, who's familiar with Mythic? Yay! This is such a friendly crowd. Thanks. Okay, so we have error mitigation. It's pretty popular. It's got like 300,000 downloads, like 100 plus contributors. Supports a variety of different front ends for quantum circuits to be written in. And our newer compiler, which is UCC, that is the Open Source Quantum Compiler Collection. UCC is meant to be a play on GCC. That is the project that I am the lead developer on. And we found, fun fact, if you combine these two things together, you can do better than either of them do separately. So that's a pretty promising area, especially because there are so many different quantum error mitigation techniques that are available in Mythic. And there are a lot of really cool circuit level optimization techniques that are available in, well, currently UCC is based on the Qiskit transpiler, and there's a lot of really cool areas of potential advantage in combining more of these optimization on different scales together. So where do we use qBraid in UCC? Well, there I was, 2024, giving a talk at UnitaryCon in Helsinki and talking about how I developed a whole quantum translator module. And then our friend Harshit gave a talk right after that about qBraid and came up to me after and was like, oh my God, we actually have like a whole module that does like the thing that you developed. I'm like, that's great. I would love to not have to maintain that. qBraid has this lovely array of different platforms that they're compatible with, different quantum circuit representations. This is very, very useful to be able to use. So we integrated that, and we are able to allow users to stick with their favorite framework when they are programming with UCC. You don't have to do any translation. You can just pass your circuit in and be like, optimize it, and then you're good to go. Okay, so Unitary Foundation community is quite broad. We have our annual Unitary Con. This was at IEEE this year. We have workshop, which is on quantum error resilience. This was earlier this year as well in New York City at NYU. And we have, as I said before, many, many active channels on Discord. We have weekly events that we host, seminars with recent papers, big authors, and also plenty of office hours for existing open source projects. Okay, how can you get involved? A quick question: who here's like an actual would consider themselves like a quantum developer? Like you spend a lot of your time programming quantum computers. Okay, cool. So yeah, if you are actively doing that kind of thing, you should definitely join our community. There's also ways to get paid to do that. So I mentioned our microgrant program, but we also have a newer thing that we're piloting, which is called Merit. Basically, this makes it easier for folks to get paid for their open source contributions. You can do this on Mythic or UCC. Those are the ones we're piloting it with right now. So those are things to keep in mind. And just, thanks to all of our supporters. We have a variety from industry and also government grants. And thanks so much for hosting us here at qBraid. So, Developer Day. And one last thing, if you're interested in compilation, error mitigation, QEC, anything like that, definitely feel free to come up and say hi and chat. Okay, thanks.
Hello. Hello. Awesome. Well, thank you. We've covered a lot of ground here today. Thank you to all of our sponsors and presenters so far.
Okay.
Hello, everyone. Welcome back to Quantum Developer Day 2025. Hey, hey. Yeah, this guy. Thank you so much. So, welcome back, everyone, to Quantum Developer Day 2025. Next up, we have a very close partner of ours, Q-Control. They're developing businesses with quantum technologies in the software and sensing space. And all the way from Australia, our dear friend Mick Conroy, staff product manager at Q-Control. Please, Mick. Thank you, everyone.
Thank you. All right, hi everyone. I'm Mick Conroy, Staff Product Manager at Q-Control, and I'm here today to exclusively announce here at qBraid Developer Day a new training offering that we're very excited to be partnering with qBraid to deliver. Now, as I said, I'm from Q-Control. You may know us from some of our other products, our multi-award-winning EdTech platform, Black Opal, our world record-setting optimization and optimization tool, Fire Opal. You might have seen Ironstone Opal, our quantum navigation solution, was recently named as one of Time's best inventions of 2025. And we're bringing all of that experience to the course we're announcing today. So this instructor-led course that we're announcing is really intended to enable teams to start solving commercially useful business problems on real devices, no specialist quantum coding experience required in just half a day. So it provides a bridge for teams that have learned the fundamentals to begin the transition to working on problems that matter to them and that are commercially relevant. So today I'm going to tell you who this course is for, what you'll learn, and how you can get involved. So who's it for? Well, I let the cat out of the bag a little bit just then, but it's for helping enterprise get serious about quantum. And what do I mean by that? I mean, helping teams go from thinking about quantum to doing something useful with quantum, jumping from that general, exploratory, more high level, hands-off, earlier phase of getting used to quantum, and then starting to transition to actually tackling problems that matter to your organization. So it's perfect for domain experts seeking to understand how quantum computing will help them. It's great for business leaders looking to understand and plan for how quantum computing is going to impact their business and their industry. But it's also for anyone who's quantum curious, those that want to get involved in quantum, but actually do something with quantum computing as well. We've worked really hard to make this as accessible as possible. And I understand many in this audience are already really experienced quantum professionals, so it's not quite for you, I don't think, but we all have broader teams that maybe we want to bring along on that quantum journey, or we have clients that we work with that we want to upskill. This is for them as well. So you can keep those sorts of people in mind as we go through this. So what is it? So there are three key products that underpin this training and make it something that's going to be the fastest way to go from zero understanding of quantum to actually getting real value from quantum devices and quantum computing. So the first of those is Black Opal. It's the product that I'm product manager for, and essentially this is the pre-work for the course. It's suitable for anybody, so you can go from absolute zero, and then you can use the really visual, interactive, engaging activities within Black Opal to learn about, what is quantum computing, what are the key things that you need to know, what are the key applications that you need to know about. Essentially, it means that anybody that wants to take the instructor level course that we're talking about, you can do the pre-work, no prerequisites required. You can start from zero. So it means that anybody can get up to the point ready to take the instructor-led course. Fire Opal, one of our other products, is also really central to how we're delivering this course, because essentially it means we can reduce an optimization problem to pretty much a single line of code. It means that anybody can take this course and get great results from real hardware, no quantum coding experience required. It means that in this training, we can focus on the problem and the value rather than getting lost in syntax and gates. And also we have, obviously, qBraid partnering with us on this. It provides a really great, seamless, simple, elegant environment for exploring the sorts of algorithms that we're working with, connecting to the hardware that we want to connect to, and analyzing the results that we're going to get back. So we're really pleased to be partnering with qBraid on delivering this training as well. So what are you actually going to learn in half a day in this instructor-led course? So I've broken this down into 5 key areas at a really high level so you get a sense of what's involved here. Firstly, it's about orienting, so setting the stage for the training, introducing the learners to some of the practical applications across sectors and domains, some of which you can see here, so they can get familiar with what's possible, but also then getting into how do you actually identify the criteria for selecting promising near-term use cases for an optimization problem that they might want to work with. Learning the high-level workflow for taking a use case from taking a use case to a problem that you can formulate and actually to a solution that you want to run. So actually learning that framework. I mentioned formulation, obviously extremely important. And I had a train scheduling problem on the previous slide there. That's actually one of the problems we really dive into in this training, and this high-level visual is from that use case. Essentially, it's about how do we efficiently route trains through a station. Here it's London Bridge Station, one of the busiest train stations in the world. And so how do you actually route these through? We're going to take all the information about this business problem and turn it into a problem that's suitable for a quantum computer from start to finish in this training. We're going to extract all the relevant problem parameters together from the real world use case. So for example, what are the expected arrival times? How long is the train? How long is the station? Are those things compatible? What's the expected leaving time? All of that stuff, we're going to take all of that and turn that into something we can then execute on quantum hardware. So execution is the next phase of the training. And FireOpal, again, is the real magic here at the heart of the training, because essentially it means that FireOpal's solvers, you can see at the bottom here of this diagram, essentially means that it offers a single, easy-to-use function for key problem types, like optimization problems, QAOA, things like that. And all the solver requires is some key parameters, including the cost function, which we just spent the previous section exploring, and then we can just run it on real hardware. We take that London Bridge problem, we take 20 minutes of real station routing data, and we run it on devices of 50 to 100 qubits within the course, and so we can work with the problem at a commercially useful scale as part of the course. Actually, Sanket from IBM kindly called out FireOpal earlier, which is also available in IBM as a Qiskit function. That's what we're using here. So everything is easy to do, everything's taken care of, no further coding required, no drowning in syntax or huge circuits. Again, the focus here, it's a short course, it's focusing on the business problem, makes it extremely accessible for absolutely anybody to undertake. Of course, we need to understand the results that we get back. So we're going to be comparing the outputs we get against appropriate benchmarks, showing where quantum computation is doing something useful as part of that, and comparing it against classical approaches as well. Here we can see FireOpal was able to find the optimal solution, and in this particular use case, which the actual use case is available on the Q-Control website, setting a world record for the largest constrained quantum optimization. Now I mention that because by using FireOpal with this train station routing problem, we're doing a similar problem here. We're working with a similar problem. We can get this world-leading performance with automated error suppression, performance optimization. We can show in this course how to get the most out of today's quantum hardware by doing it in the course of a similar size. So we're focusing on performance and output here because for the sorts of people in this course, the domain experts, the business leaders, looking at quantum's potential, performance equals cheaper computation. Performance equals higher fidelity results. And that means you're more likely to be able to deliver business impact sooner. And sooner is important because the most common question that we get, I'm sure we all get, is when can I see quantum advantage for my use case? That's a pertinent question, but it's a question that you can build a roadmap for, given the sorts of quantum hardware roadmaps that were shared earlier from the likes of IBM. We can take a given problem and we can forecast when we can start to expect to see outperformance of classical solutions. So for this scheduling problem, using FireOpal, we can expect that we'll be able to outperform classical approaches as early as 2028. That makes the value tangible to the sorts of business heads in the room in this training, because you can see, all right, the sorts of problems that I'm interested in, I can put together a similar forecast, and that really crystallizes when you can start to see value, when you can start to see a commercially useful solution for whatever problem that you're interested in. So that's been a really quick overview of the sorts of key outcomes we're looking to tackle in this training. So everybody that comes on this course will leave with the framework for tackling these sorts of problems. They'll have been exposed to the tools to be able to tackle these sorts of problems, and they have all the context necessary to be able to move forward and work on whatever it is that interests them for their organization. So that power and simplicity of Black Opal, Fire Opal, and qBraid make this, one of the best, fastest ways for organizations to do that. And again, suitable for anyone, low code, real hardware, real use cases, and in just half a day. So if this sounds like something that's of interest, we are opening course registrations from today. We'll be running the course starting in early 2026. You can pre-register to get access to a really detailed curriculum for anybody that wants to see exactly what you'll be learning rather than the extremely quick overview that I've given today. So we've got the QR code there. We've got a link. Come and see me at the kiosk outside as well if you'd like to get an actual cardboard flyer. So we're interested in anybody pre-registering, but we're also interested in partnership discussions. So anybody that wants to help to expand the actual delivery of this training even further, hardware partnerships, whatever it is, come and chat to me as well. So with that, thank you very much for your time. I look forward to talking to each and every one of you outside or in drinks later, and enjoy the rest of your afternoon. Thanks very much.
Thank you for that, Mick, and we're so excited about our partnership with Q-Control. Next up, we have an academic lecture coming from Professor Charles Yuen at UW-Madison. He is sharing his presentation on programming systems for quantum applications. Please welcome Charles Yuen.
Great. This microphone, does this work? Testing, yeah. Great. Hi, everyone. I'm Charles, and I'm really excited to be here today. I wanted to thank the organizers, everyone at qBraid, for putting together this awesome program. So, I am an academic, a computer scientist by training, and so this talk is going to have a bit of a different, more scientifically flavored vibe to it, and I hope that what you get out of it is an idea of some of the specific technical challenges that we still face in implementing complex quantum algorithms, and some ways that we might overcome these challenges. So to start, I would say that my research is really grounded by the question of how we can realize the promise of quantum computational advantage. And I'll get right to the heart of that question, which is in the realizing part. Because a lot of people are, of course, under the impression that the day that we have a billion qubit machine on our desks, we'll be able to simply implement all of these algorithms that we see out there, and that this is going to solve the whole problem. How hard is it actually to turn a theoretical algorithm, the kind that you might see in an archive PDF paper somewhere, into a program, a sequence of executable instructions that actually works correctly with the hardware that we have? Well, to understand how hard that might be in practice, let's put ourselves into the shoes of a programmer tasked with implementing something like Shor's algorithm for factoring numbers. Now, if you flip open the paper to try to learn what each step of the algorithm is doing, you'll typically encounter something that looks like this, a mix of English and math and pseudocode telling you what every step does. Now, I'll go ahead and summarize for you what this math in this part of the paper is saying. It's actually having us compute an operation which is modular exponentiation. Okay, so we're given two integer registers, a and x. We want to compute x to the a mod n. And the way that the algorithm will do this is that it will repeatedly iterate this process of multiplying by x mod n. And it will do that a times. Now, I don't know about you, but as a programmer, whenever I see this kind of iteration pattern in an algorithm, I tend to reach for something like a for loop. And indeed, I claim that if this were a classical program being written on a classical computer, it would probably take about one line of Python to realize. But how hard do you think it is to implement this part of Shor's algorithm in a state-of-the-art quantum programming framework? Well, that's the code to actually implement this part in Microsoft's Q# language. Right? The text is very small. We can blow it up a little bit and see where this complexity is coming from. And it comes from the fact that Q#, like most competing circuit-based programming frameworks out in the world from every major vendor now, gives the developer the abstractions of working with individual logic gates, individual qubits that you can, execute bit flips on and phase gates on, condition on the values of other qubits. Now, this is pretty comparable to, in the classical world, what hardware designers do when they write Verilog or VHDL. Okay? What the program is doing is it's describing an object known as a quantum circuit, right? I mean, here's a complicated example of a quantum circuit I got from a paper. You can see it's got the same kind of abstractions. And what a quantum circuit does for us is that it gives us a standard by which to communicate algorithms and program quantum computers today. The problem is, I think that this is hardly a practical or scalable way to get people into quantum computing. I mean, it's a tremendous barrier to entry. For anyone who's not an author of one of these papers, you're going to have a hard time figuring out exactly what is going on. And so the problem here is that we really don't know how to program a quantum computer to practically realize many of these algorithms. Specifically, we lack all of these wonderful programming abstractions that we've come up with for classical software over the last 50 years or so. And the fact that there exists such a large abstraction gap means that in practice, every single algorithm that I have shown you so far in the slides now has never actually been explicitly written down as a program that could execute concretely on a quantum computer. Now, the reason that this gap exists is not just because quantum computing is in its infancy and we haven't had enough time to think about the problem. There are a lot of fundamental technical challenges here. And what I want to tell you about in the remainder of my time is how my research answers the question of how we can practically realize these algorithms by building abstractions, tools, languages, compilers, libraries, runtimes, analyses, all of these sorts of things that we rely on every day for classical software that we're going to need to reinvent for the quantum world. So let's get a little bit more deeply into some of these algorithms. And I want to tell you a little bit about some research that we've done on inventing the concept of a data structure on a quantum computer. So here's the setting. All right, we want to implement these amazing quantum algorithms for search and optimization. You can read the papers here. They're doing things like solving the subset sum problem or closest pair from computational geometry. And they're giving these awesome speedups over the best known or best possible classical algorithms. But what makes these algorithms very difficult to implement, and you can see this from the papers themselves, is that they rely on the concept of a data structure. Something like a set or a dictionary. These sorts of things that we, again, use every day in Python. But what does that even mean on a quantum computer? I mean, how could you possibly make these qubits behave in a way that a list or a dictionary or something like that works? Well, if you think about it for a while, you can come up with a way to define this. I mean, I claim that the notation on the slide here is some quantum notion of a superposition of a linked list. And you can translate these objects, these list here, to individual bit patterns that are going to be represented by the qubits in your machine. And the problem becomes, well, how are you going to implement all the operations that your programs are going to need? The ability to push to the front of a linked list, compute the length of a list, okay, these sorts of things that we're going to have to implement as circuits. Now, you might think, naively, that we can just take our CS 101 approaches here. Right? We're all taught, I think, what a linked list or a binary tree or a hash table or these sorts of things are and their asymptotic complexities. And it'd be great if we could just take these things, compile them into circuits, run them on the computer, and that's the end of our story. The problem is, that doesn't work. If you actually take these CS 101 approaches, it will cause the algorithm to provably lose all of its computational advantage. Its performance will degrade to become no better than a classical randomized algorithm. There are a couple of things that we need to do to solve this problem, come up with a new programming language and abstractions and ways to lower those abstractions onto hardware. But what I want to do first is dive a little bit into why this won't work. Right? So there are turns out two formal properties that we need to satisfy if we want to implement these data structures. They happen to be called reversibility and history independence. Reversibility comes in a phenomenon like this one on the slide here. So what I want to do is I want to implement a function called pushFront that pushes to the front of a linked list. And here's an example of an input-output pair that I want to satisfy. If I start out with a superposition of a list and I want to push a superposition of elements to it, I should end up with a superposition of the list. Input superposition, output superposition. Now, I claim that you can't actually do this correctly using just some naive C++ code, the way that a classical programmer would approach this problem. I mean, here's some code that would do it. Allocates a new linked list cell on the heap, dereferences some pointers, returns the pointer to the new list. This code should hopefully make sense. But why would this code not work in a quantum setting? Well, what does it actually do when I feed it the inputs in superposition? It gives me back a superposition of not only the data that I want, which is the final list, but also some auxiliary garbage information, such as the original list, and also this tuple, that's some temporary value that I accumulated. Why is this a problem? Well, it's because a key property of why quantum algorithms work in the first place, why they give us any advantage over a classical algorithm, is something called interference, which states that if I have a superposition of two pieces of data that have the same bit pattern, but equal and opposite signs, then they should cancel out. They should go to zero. That means the quantum algorithm will never sample that piece of data. Narrows down its state space exponentially compared to classical algorithms, right? But what happens if we take this interference equation and muck it up by adding some garbage data? Well, look, 0, 1, and 1, 1 are not the same state. They will never interfere with each other. And the result is that if you use this in your algorithm, the signs, the interference, the quantumness, all of that goes away. Performance degrades to be classical. So how did we solve this problem? Well, I won't bore you with the technical details. It turns out that what we need to do is to come up with new programming language abstractions that don't have this property that they ever leave behind garbage. Right? So whenever there are temporary variables in your computation, the program itself is responsible for cleaning that up. So for example, in the correct version of this program in our language, which is called Tower, at the point where a temporary variable comes in, the programmer will insert a statement that uncomputes that variable. Uncomputation, for those of you who don't know, is the opposite of computation. If you think of computation as a process of taking a 0 register and flipping some of its bits so that it stores a value that you like, then uncomputation is the process of flipping those bits again so it goes back to 0. And when it's back to 0, that means it won't interfere with your interference. And that means that the algorithm will be able to work correctly. So we'll have a construct such as that one, which in this case is just a mirror image of our conventional assignment operator, which takes the right-hand side and puts it into the left-hand side. In this case, we're getting rid of the left-hand side using the right-hand side. There's another thing that we would have to do in this case, which is to think about the way that we dereference pointers. If you dereference a pointer in C or Python and store a value into memory at some address, what is happening to the old memory that used to live at that address? Well, in general, it's being erased, right? It's being overwritten. And if you know anything about quantum information, well, it really doesn't like that. Okay, unitary operators do not like it when you try to do things like this. And so in our language, we're going to have to come up with a way of dereferencing pointers, in this case, swapping them reversibly with a local variable so that no information is physically lost. Turns out that if you do this, you can actually construct these programs in a way such that by the end, you do get the thing that you want. In this case, it's the list with the element pushed to the front of it. And the whole thing is reversible. You can run it actually backwards to go from the output back to the input. And that mathematically guarantees that your program will compile to a correct unitary quantum circuit, will enable the quantum algorithm to get the speed up. Believe it or not, that isn't even the end of the story. There's another property that we need to satisfy here, which is called history independence. So here's the problem. Imagine that you have a program, a quantum algorithm, that has two variables in it, S1 and S2, which are both intended to denote the same piece of information. In this case, is a set, 1, 2. The interference equation would have you believe that they should cancel out and go to 0. But what could cause this to go wrong? Well, how do we actually implement sets? What if we use a linked list, as is very typical in Python, right? If you use a linked list, it could happen that depending on the order of operations, the order in which you've inserted the 1s and 2s, you actually get two different bit patterns that once again do not interfere. You might think, all right, let's just solve this problem by sorting and duplicating all of the lists. Very simple in theory, but you need to look deeper. Because even these two identical looking linked lists can have two different physical representations in memory. Every time you call malloc on a classical computer, you get a pointer back. Who knows what the value of that pointer is? Now, the quantum computer cares very much what its value is, and so we're going to need to make it so that every instance of a data structure actually has a unique physical representation for these algorithms to be able to work. There is, fortunately, a way to do this. You can actually exploit superposition here. You can define the representation of this data structure to be the uniform superposition of all of the ways in which it's laid out in memory. This satisfies the math, and it makes it so that the quantum algorithm does get an advantage. What do we do with this at the end of the day? Well, we actually built a library of data structures, the first quantum library of data structures that enables developers to implement algorithms such as the ones we saw on the previous slide for the first time. We show that everything we did here satisfies the asymptotic complexity requirements that these algorithms are making in the first place. And you have to take my word for it because we actually built a compiler that takes these programs all the way down into circuits, gives us precise resource estimates for how long these things are going to take, and saving the developer the time that it would have required them to write out all the thousands of logic gates while trying to satisfy all the correctness conditions that I just explained to you. All right, I want to briefly tell you a little bit about how to go further from this work, how to make it so that we don't have a program that is not just correct in theory, but also efficient in practice when we run it on quantum hardware. Because when we did the original work, we made the assumption, as many people do, that we're going to have a fault-tolerant quantum computer, and that error correction is going to be handled for us very transparently. Now, there's of course good news on the error correction front. Basically, every company is now aggressively pursuing the ability to scale up our exponential suppression of noise using redundancy. But the question is, when we take a predominant quantum error correcting code, like the surface code, what happens to the performance of the programs that we're studying here? I mean, here's an example of a program. I won't explain it in detail, but I just want to convey the idea that if you're going through a linked list to find out how long it is, that should probably take time linear in the length of a linked list. All of algorithms are going to assume that. It would be a shame if that assumption were to not hold in terms of the actual number of logic gates that it gets executed on your physical quantum computer. And guess what? That's where I've got bad news for you, which is that this program, when compiled to the surface code, is actually going to take quadratic rather than linear time. That's obviously really bad because if your algorithm is only going to give you a polynomial advantage, you certainly don't want to shave any of that off during overhead in the compilation process. Now, the scientific question is, what could cause this discrepancy and what might we do about it? Well, in our paper, we identify firstly that the problem here really is control flow. The quantum version of an if statement that branches over a qubit in superposition to decide whether to do one thing or another. It's a very simple idea, and yet it turns out to be profoundly inefficient to realize on a lot of error correcting codes. For now, one thing that we do to help our programmers is to give them a correct analysis that they can use to conclude that this thing actually has quadratic rather than linear complexity. But more powerfully, based on those insights, we actually give you a compiler that rewrites this program to a form that when compiled to a circuit for the surface code will still take linear complexity to run. By the way, how much time do I have left? Because I know we started a little late. Okay, great. I'm just going to finish up then by saying that, here are some of the questions that still really keep me up at night in terms of research. The first one is, how are we going to make a lot of these algorithms and their asymptotic promises actually pan out on hardware? It's no secret that just taking 2 to the n cubed or whatever, that's not going to be enough. We need to lower the constants as much as possible. We need to engage a lot with the compilers community to figure out what the quantum version of loop invariant code motion is going to be to systematically reduce the cost of these algorithms. The next question that keeps me up at night is whether it will ever be possible for someone to program a quantum computer without being an expert in quantum mechanics. The thing is, we've actually done this in computer science before. We've done it for parallel computing and probabilistic computing. You can install OpenMP and have this compiler pragma that you just insert in your program. And even if it's not perfect, it lets you run programs faster on a parallel machine than on a sequential one, right? Is there a quantum pragma that we could ever hope to insert into our programs to just give people the key to speed up. Well, by this point in my talk, hopefully it's clear that that would be very hard to achieve, but how close can we get? That's still an ongoing scientific question. And, I hope to chat with you all to see what sort of ideas we can come up with for making this technology more accessible for everyone. Thanks.
Thank you, Professor Yuan. That was very, very insightful. We'll love to take a look at the data structure library. So we are now doing just a brief sets change. So please bear with us one moment while we bring these tables on stage here. And now I'd like to welcome Professor Laura Gagliardi, the Richard and Kathy Leventhal Professor of Chemistry and Molecular Engineering at the University of Chicago. Professor Gagliardi is a leading voice in quantum chemistry and one of the world's most cited researchers in the field, so we're just so lucky to have her here today. Professor Gagliardi will be joined by her doctoral student, Joanna Wang, and IBM research staff member, Mario Moda, to discuss quantum and material sciences for energy. Thank you.
So, everybody, I'm very excited to be here today. So I'd like to thank qBraid for this invitation. But what is more exciting for me is that I've put together an amazing team. I have my brilliant student, Joanna Wang, and Dr. Mario Motta for IBM Quantum, who got permission from his boss to come here for this event. So this is really amazing. And what we are doing together, sorry, this is not the beginning of my talk. It's here. This is the first one. So what I think that it's important to have this type of teams because I know a little bit about chemistry and computational chemistry. I work with brilliant students like Joanna to try to exploit the best architectures, classical and quantum. And then we work with Mario. And I think that if one wants to address, and not just Mario is an example, but I will also mention collaborations with Yuri, with qBraid. If we want to address important problems in energy, I don't know why the first slide of my talk doesn't stay. I don't know. I'm not trying to move it. We need these teams with different expertise, and there is a big push in energy. We know this nation really wants to achieve the best in energies, and here I'm just showing an example, and I apologize if this talk is a little bit too chemistry oriented, but I am a chemist at the end of the word. Converting natural gas, in particular methane to methanol. There are many sources of methane, and methanol is a very important fuel that can be used for many applications. But this conversion is tricky. It's difficult eventually if one makes methanol to conserve as such, transport. And if one can solve this problem, we would all go to Stockholm to get the Nobel Prize. But actually, I want also to tell you about the fact that chemistry can be used in material science, these challenging problems. And this year, actually, the Nobel Prize was awarded to these three brilliant individuals for the discovery of metal organic frameworks, which are materials that really are formed from molecules. So in a way, they bridge the chemistry universe with the molecular universe. They are these reticular frameworks with inorganic units, these metal oxides, connected by organic linkers. And what is interesting is that you create these reticular structures with a really high internal surface area. If you take one cube of these porous materials, and you unfold it on and just look at the surface area available, it covers almost the entire surface area of a soccer field. And here, this is I like this. It's fun. The citation from the Nobel Prize. I mean, by choosing these components, you can create these sorts of apartments, and you can have an apartment for each type of molecule. So if you want to capture water or CO2, you will have a different apartment. So why computations? And we heard a little bit about using quantum computers for eventually computational chemistry. We know that experiments only provide part of the story. Computer simulations can fill information gaps, offer interpretation, and suggest new targets before their synthesis. And especially if we look at these structures with bond breaking, bond forming, we need quantum mechanics to describe the electron distributions. So I will show you very briefly a case study, and then we'll see how we can go from classical to quantum in the simulation. So there is this particular MOF called MIL100, which could be a good candidate for this conversion of methane to methanol. And there is this metal oxide node. The initial synthesized materials as 3 irons. But of course, on the computer, what we like to do, this is what we do all the time, is, for example, change the composition of this metal oxide, replace some of the irons with either transition metals, look at reaction pathways. So this is the catalytic cycle for the methane to methanol conversion. And this on the computers is how different transition metals would change the reactions barriers and make this conversion more or less feasible. However, I mean, the workhorse for this type of calculations is density functional theory. But these are systems with a very complex electronic structure. There are some open D shells, F shells, and we talk about near degeneracy electron correlation. And so one needs to go beyond Consham DFT, but of course, as you know, full CI has the exponential scaling. So one of our goals in our research is to try to develop methodologies that don't have the unfavorable scaling of full CI, but that can still describe these situations of near degeneracy. And my group has been working a lot with the idea, again, thinking in a chemistry way, that also electron correlation sometimes is not totally delocalized. There are, we call pockets of electron correlation. And here you see this, again, the metal oxide that we were looking at before. Maybe the electron correlation is localized on the transition metals. And the same for these long chains with aromatic compounds or nucleobases. So can we think about a wave function that has full CI features or quasi-full CI feature on the local pockets, but overall it is a tensor product of different full CI features on the local pockets. And so ideally, this is a method that Matthew Hermes in my group developed. And ideally here, the exponential scaling is only within each of these wave functions. But this wave function scales linearly, ideally, with the number of fragments. And so we are exploring this concept and algorithms on the classical computer, but also we have been thinking whether this type of methods can benefit from a quantum architecture. And this has been a collaboration with many people in the past few years. You can see some of them here are actually present in the room, Yuri Kanav, but also Steve Gray and Matt Otten. So the idea is you have this extended system, you fragment, and you want to have a sort of full CI wave function on each fragment. And for example, one could use a QP and then recover the interfragment correlation with, for example, unitary couple cluster, which can be optimized using VQE. So in a way, these fragmentation methods merge the best of the quantum world, because they exploit the quantum architecture to recover the interfragment correlation, but also instead of doing a full CI on the whole system, we do this localized full CI, and so the problem becomes less expensive. So now I will give the floor to Joanna first, who will talk a little bit about the work that she's performing in collaboration also with Mario, and then it will be Mario's turn.
Thank you so much for the wonderful introduction. So, oh, sure.
I can move the slides for you.
Okay.
No,
Okay, I'm just gonna stand here. Yeah. Okay, I can.
Just tell me next.
Okay, thank you. Yeah, so here's another example of how we combine near-term NISQ algorithms with wave function, or specifically fragment-based wave function developed in our group. So in this project, the method we use is called sample-based quantum diagonalization, or SQD, which I think was mentioned earlier. So essentially, the idea is we sample configurations from a quantum hardware, and then we do classical post-processing, and then finally we diagonalize in a subspace from these samples from the quantum hardware. And in this specific algorithm, we try to come up with alternative ways to solve for the fragment wave function. And as example shown there, we have an erythropoietin molecule, which has one fragment of 26 electrons and 24 orbitals, which is not doable with the pure classical last theory. However, with the help of SQD, or the quantum hardware, we're able to actually solve fragment sizes beyond what's capable from direct diagonalization. And in return, the sort of fragmentation also allows us to have shallower circuits, which means that we also have less noise accumulated. And this method, which we call less SQD, really is a framework for us to interface with the current hardware that we have. And we build this sort of back and forth classical quantum loop. And it is really a way for us to understand the current limitation. And also, I believe that the results will only become better from here. So next, I'll have Dr. Morimoto, which is a very close collaborator with us, to talk a little bit more on pre-fault tolerant and fault tolerant futures.
Thank you. So a couple of extra words, thank you, about Joanna's work and choices underneath. So why using a method like SQD? No, so for example, we know that, I think everybody here knows very well that qubits undergo decoherence, there are errors in quantum gates, and so those translate into limitations in what quantum circuits we can do and get results of quality out of it. Now, today, what we can do is essentially try and mitigate these errors as much as possible, and SQD is a form of error mitigation, for example. That is useful for the applications Joanna and Laura care about. Now, of course, one of the goals that everybody's aggressively pursuing is fault tolerant, wherein we don't cancel the errors, we ideally correct them in real time as they unfold. And it's very complicated, very challenging, as it was brought up before, and it's not like one day, September the 4th, 2027, all of a sudden the errors go away. There's transition accompanied by many challenges. We are compilation. For me, one is that there will be a time in which limited redundancy is used to lower the logical errors, and the surviving errors will still have to be mitigated. So groups like these are using NISQ devices and error mitigations also as a prelude to enter in this phase. The thing that is interesting for me, I confess, is what's going to be the nature of the logical errors. Will they be more local, more dense than the ones we have now? Scientifically, I'm looking forward for that. So this sort of change in the platforms is also translating into the algorithms that we can run. So they have to run something like SQD, which is heuristic, because ideally we would want deeper circuits, more gates, so we can synthesize more generic wave functions for chemistry calculations. But those wave functions are also suffering from noise. And so, for example, they use this method, which uses the quantum computer sort of as a slot machine that gives you electronic configurations and then a classical computer to do error mitigation and diagonalization. Long story short, this is a heuristic method, and groups like these do something extraordinary, which is perform non-asymptotic numerical analysis, so they can know for sure is this method good or bad, in relation especially to properties of interest. And it's always transformations in chemistry. And then, of course, as one progresses towards more coherent devices, there will be other algorithms that one will be able to run. Again, the fact that there isn't just a discontinuous jump in the hardware should be mirrored in the algorithms. So, for example, even a sophisticated algorithm like phase estimation will always require an input state, and that can come from a classical calculation or from some heuristic like SQD or something else. And there is not just a discontinuous transition from phase estimation to the heuristics. Important thing is always use classical and quantum computers together and get the best out of each, and try to have as continuous a path as possible also in the space of algorithms to track the development of the devices. And I give you back the floor.
I will just say a few words to conclude, and then I hope there is a little time. We wanted to leave a little time for questions. But I want to go back for a second to quantum chemistry and tell you that one thing that is really now the most popular thing to do is to develop machine learned force fields using some quantum chemistry data. And of course, DFT, again, is the workhorse to do this development. Here is an example of a paper by some colleagues, which was great. I mean, they study surface diffusivity and then to decomposition on this iron. And there was a commentary that said, this way to develop machine learned force field is adequate for this problem. But when there are open shell structures like metal organic frameworks with partially filled D or F shells, DFT is not sufficiently. And nowadays, I can tell you that all the literature is training these force fields with DFT and with crappy functionals. So that is another comment that, so among the possible functional, the worst because it's the cheapest. So I think what is important is to develop, to train force fields with this more rigorous wave function-based force field. And this needs smart methods, but also smart computers one way or another. And so, for example, in this particular study, we have totally trained a force field on these post-DFT methods. And now one can perform dynamics for catalytic reactions in a very accurate way, but for long durations. These are timescales that are not affordable with conventional calculations. You need the machine learned force field, but you need to train it on these methods. The other point that I want to discuss is that, I think quantum, I was one of the ones who raised the hand about skeptical in the previous session. I think they are an amazing opportunity and territory of exploration. But when I read papers of my colleagues who say that with quantum computers, they solve all the energy problems, all the health problems, I think it's a hype that will only damage us. So we have to be honest, just work hard and make progress day by day. So if we want to achieve a quantum leap, and by the way, in this case, just really make progress, we really need to be aware that we are treating phenomena at different scales and we need consistency. We need to develop better methods to model the complex systems, and that's why we have bright students, postdocs, better algorithms for all the computers of today and tomorrow, and also work together with the experimentalists, collect as many data as possible, so high throughput experimentation and computation. And this is my group. I'm just here to tell you what they do, but also I want to also acknowledge all the people with whom we have worked in this journey, especially qBraid and the sponsors, and all of you for your attention. And I think we left a couple of minutes for questions, right? Thank you so much. Too much chemistry. You have a question? I know.
No, I have the mic.
Well, maybe, okay, there is a question there. Yeah.
I've read these review articles that have said, you know, like, okay, for peak distributions, you know, quantum won't give any speed up for many different kinds of chemicals that we thought would give speed up. We actually don't, because now GPUs are really good. So what are the fields or you know, spaces of chemicals and materials that you are excited about when it comes to quantum, using quantum to do the calculations?
I mean, I think that maybe quantum has a potential to give accurate energetics and an accurate wave function for these systems, for example.
Yeah, the metal organic
But again, chemistry is about change. So it's not just saying, okay, I run a calculation on a metal organic framework. You have to study a reaction, do a dynamics, and see how. So if you can compute the wave function accurately along a chemical transformation, that's a great potential. The problem at the moment is, maybe Joanna can comment, or Mario. Okay, they develop these beautiful methods, and then I say, okay, let's study a real system. And no, we are always back to our toy models. Maybe I'm just impatient. It's just a matter of time. But I think, I'm not saying that there is not a potential. I'm just saying that the problem cannot be solved now. Maybe Johanna and Mario want to comment? Sorry, I put you on the spot.
No, that's okay. So yeah, so maybe my perception, which could be completely wrong, is that in a discipline like electronic structure, much of your understanding is based on approximations. Cioè, quantum computers, they have arrived a few years ago, but for decades, classical computers have been introducing different approximations for wave functions and so on. And there is only so much that mathematical and theoretical arguments can tell you about the real performance in a real situation, unfortunately. As far as I've seen, the chemists tend to develop understanding of how these methods really work through extensive non-asymptotic numeric analysis. There isn't a theorem that says couple cluster can do this and that. The very few inequalities I've seen, especially in exact diagonalization literature, are this very loose. Okay, yeah, good, I have an inequality, but it's orders of magnitude worse. So I think it's natural and healthy to try and get as much hard evidence by data. And it's a complicated thing because the space of algorithms that we can access is constrained by the resources that we have on the devices. And so what we have to do is grow day by day. The important thing is to keep growing. Aside from that, and I comment, but I might be wrong. If you ask me what excites me, what I'm waiting for, is not so much maybe the ground and low energy excited states of electronic wave function, beautiful, but also I think the dynamics. A quantum computer, for me, is a machine that propagates wave functions in time. No, that's the Feynman vision, if you want. And so for me, it will be taking a quantum system, peacefully lying in the ground or in the thermal state and attacking it with some disturbance, like a strong laser, and seeing how it responds to that. That's where I think the interest is gonna lie, at least my interest. That's it.
There was another question.
Yes. So Sean here from Purdue Northwest. This may be a very rookie type of question. You mentioned that they're training the machine learning model using DFT. I also heard, now DFT you mentioned that do not have good resolution, basically the shell. They have problems with the shell, so the accuracy rate is probably not that great. I also heard that there's the Hartree-Fock, which may give you better accuracy or resolution of the the structures. Is that the case? Is that? But you also mentioned DFT is cheap, so Hartree-Fock is probably more expensive. But would it be possible to develop a machine learning workflow to so the idea is to probably introduce some distillation here. So you have cheap, abundant DFT data. You have probably more expensive but less abundant Hartree-Fock data. So maybe somehow there can be a machine learning algorithm that can tap into the advantages of both and can probably speed up the learning. I'm just totally throwing this question as a rookie.
Thank you so much. So actually, I think Hartree-Fock is less accurate than DFT. Again, in DFT, there are various flavors and it depends on the problem. But there are, for example, functionals that have a little portion of Hartree-Fock and they are very good for certain problems. So I think perhaps the comparison should be done between DFT and post Hartree-Fock, so improving on Hartree-Fock in the wave function world. And certainly what you said is that we cannot just do everything with full CI. We would have to do dedicated treatments for the portion of the problem that cannot be solved with DFT. And these hybrid approaches are certainly the future. But again, one is to know when DFT is not accurate enough and how eventually to develop these hybrid treatments. Are we done with, are we late? How are we doing with that? Okay, well, we are around. If you have other questions, we are here. Thank you so much.
Like 2 minutes. So yeah, just a very, very quick announcement, everybody. First of all, my name's Kenny Heitritter, VP of R&D here at qBraid. I just wanted to announce a couple cool things that we have going on with respect to GPUs on qBraid. One really cool thing that we've been running over the last few months is this GPU for Quantum challenge that we've had. We actually have one of the participants and winners here today with us. So today we just wanted to announce the people that we selected as the winners of this competition. It's this Q-Vengers team. The people who participated in it are Andrew, Marlon, Andre, and Vlad. And we'd really like to congratulate them on a really, really great job. Well done on this challenge. They came up with and used a GPT QAOA style application to financial optimization problem. Yuri Alexeyev, who's actually here today, was the author of one of the original papers on GPT QAOA. So Andrew, I'd recommend you talk to Yuri. So thank you very much to them and to all the participants of the GPU for Quantum Challenge. And then along with that, we're very excited to be bringing GPUs out of beta on qBraid. So actually a big part of the GPU for Quantum Challenge was rolling out some beta access to low-cost scalable GPUs on qBraid, fully packaged with all the quantum software that you want right out of the box. So we gave a good number of credits and access to all of these GPU for Quantum Challenge participants. They used it and developed everything that you see that's on this repository. So we're going to be rolling out fully scalable Blackwell instances all the way down to like V100s and A100s very, very soon. And yeah, we're excited to get them in the hands of all of you. So just wanted to throw that out there. Yeah, please give it up for the GPU for Quantum Challenge winners. That's all.
And next up, our final discussion here. Don't want to keep you all from dinner here shortly. We have a brief panel with a few leaders in the quantum software space. Please welcome Sanket Panda from IBM, Robert Laredo from Entangled Solutions, and Jordan Sullivan from the Unitary Foundation. And so much of the discussion here today, I love the comments from Quantum Rings on being a bearable, but I see quantum software often being compared to classical in the sense, right? And we have this history of classical computing software, which gives us these great directions to then articulate quantum software. And so I'd ask, how do you see the quantum software stack evolving from circuit level programming to high level workflows over the next few years?
Yeah, I can start to speak to that. I think we're starting to see a lot of folks who are in the quantum space formerly focus on this kind of lower surface circuit level work, moving into these higher level representations. You know, you have Qiskit functions, you have companies like Classic. There's plenty of people who are focusing on this higher application level. And you also have people working on circuit level optimization. And I think what we're starting to see, and what I hope we see more of over the next few years, is getting into this really messy, knotty area in between circuit level optimization and like actual device level control. When it comes to the kind of compilation that you need to do error correction, you need dynamic circuits, you need different types of control for different devices. So as it evolves from this kind of two levels of like high level abstraction, circuit level, you know, we're doing Boolean logic operations, then getting into this really, really complicated stuff. So that's what I would say.
You know, when I see how Linux and you know, typical software gets developed, right? It's not like one day you just randomly had an interface and then all kernel level development just ceased to exist, right? Exactly what Jordan was pointing out. I think that over time you have more and more abstractions forming. The lower levels of the stack, like you guys probably could guess, is still elements of research. And you know, these abstractions themselves, like Qiskit functions, where you have partners like qCTRL, you know, building up abstractions, you still have each of these abstractions have control and data, right? That's the foundation of a good abstraction, right? Each of those evolve over time, and each of the lower levels of the stack, you propagate data and control upwards as well, right? I think that more abstractions will develop as more of the lower levels stabilize, and performance guarantees are known, thing number one. But that is going to continue, at least I hope, quite like how typical software developments in Linux and others have progressed until this point. So I don't see it as like a one or the other as much as more interesting and fun things are going to continue happening further up.
Yeah, and I think in that same context of everything kind of bubbling up, right, from the lower level qubit, compiler, transpilers, et cetera, moving up to the abstract level of integrating into workflows, that is what's kind of what where the I would say it's building up to, right? Initially, 5 years ago, everybody was talking about just qubits and how do we wire them and how do we build these circuits, et cetera, et cetera. Now we're at the abstract level of looking at applications. I think one thing is we're looking at it from going from bottom up, right? But I think once we hit that top, which we are basically looking at now with platforms and everything else that are working, I think now we got to think about it's going up, but then it's got to go out. And more specifically, how do you integrate into these systems? Okay, like Dr. Yuan mentioned earlier, right? He says we're looking at some data structures. You know, think about it from the people that aren't in quantum, that are building these, different algorithms, or they're building applications that are outside of quantum that might want to be able. I mean, they won't have that magic quantum button yet, but eventually they're going to want to have something similar to that. How do I easily integrate into these systems? Is there a platform? What does my IT staff have to do to integrate into your systems? HPC components, all of these sort of things, right? Whether they're buying a system or they're accessing it through a cloud or through a platform, what are the considerations they need to do in order to be able to integrate this also somewhat seamlessly without having to drill down and have to go to the bottom and try to figure everything out all the way up?
Yeah, these are really great points. We're discussing the abstractions, making it more accessible, really the developer experience. And I think there might be somewhat of a misconception in that a physics background might be required to work on some of these algorithms. And so for the industry to truly expand, I wouldn't see it as users and developers needing to be truly dedicated physicists. So what would need to change in terms of tooling, languages, or infrastructure to make quantum software more accessible to those outside of just a physics domain?
Yeah, and I think kind of just building on what I was just mentioned, think about everything. We have to think about things from a top down now, right? Rather than, I mean, every presentation you've probably seen in quantum starts off with, what is a qubit? What is quantum computing? Why not start with, what are you working on now? What are the complexities that you see? Start at the application level, the workflow level, the abstract level, in a sense, right? Now look for those particular problems or challenges that they have classically, some computation, because really we're just talking about computation. What are the computational aspects of this? Okay, now which of these particular applications can I help you speed up, or can we work together to kind of accelerate these particular components? Where are the abstracts? In fact, the panel that was up here earlier was talking just about that. They said there's a lot of existing stuff that we use classically that are pretty much approximations. They're the best guess, right? Now, if we can come up with a way to come up with something that's more concise, and be able to say this is very accurate, or these are brute force type of computations, but much more, or maybe just larger scale. From that application level, having those discussions, bringing it down, is where you don't necessarily have to be a physicist. However, you're starting at a point where everybody can kind of understand, excuse me, get the gist of where we are, what the problems are, and then you start going down into those layers. All right, who am I talking to? Who needs to understand what? Because even now with computation, when we went from CPU and now we have a GPU, people jumped on it. Initially, it was video game operators, right? It was a GPU, graphics processing unit. Now somebody just said, hey, you know what? I can use the same computation to use in machine learning. How do we figure this out? Well, let's do that. Now that's pretty much everything to a whole different scale now. So those are the kind of things we have to think about to be able to kind of get that level of understanding and then obviously usage of the systems.
So if it's something that, at least at IBM, we've been thinking about for several years, right? We open sourced Qiskit back in 2017, I think. And a lot of it was, how do we start off by getting developers of any kind, physicists or otherwise, to work with us on Qiskit. One of the things I think we've realized in this journey is it's working with developers for the types of problems that they care about, that the level of abstraction that they do care about. That's thing number one, right? That's why we work so hard with our ecosystem to develop those abstractions and offer up it so developers who aren't necessarily focused on error mitigation suppression can focus on their problem, right? You have modular abstractions, as it were. that's thing number one, right? Like, how do you get, how we've seen at least more developers who are non-quantum focused to start playing in that space. Thing number two, though, I think is not necessarily tooling or infrastructure, it's access, right? It's access to systems to actually run experiments, try out something that your software is doing, right? You have to have a large enough quantum system with multiple of them, and you're able to give it out for free, right? Then and only then can you actually have developers touching it, playing with it, breaking things, iterating, and then offering up new software, cool software.
Yeah, I'll just briefly plus one the last thing. It is, I don't think it can be overestimated just how much of computer science has been discovered by people just messing around, just like, oh, but what if I did that? But what if I tried that? Okay, this is so stupid. Let me just try. And, the way that things tend to get developed, a lot of it is trial and error. And as we were just hearing from the kind of quantum chemistry perspective, it's like, yeah, we would love to try out like all these algorithms and like try out quantum computers for, the actual full wave function evolution, but like there's no machine that's anywhere close to good enough to test that. So like we're back to our kind of approximations and classical methods. And I think that there are a lot of areas in quantum that as we are able to expand access to higher quality devices, people who are not already quantum experts are able to get meaningful data out if they want to, mess around and see how far they can get.
Yeah, and to go even a little bit more in depth on that, Jordan, I can tell you have such a passion for open source software. Of course, shout out Unitary Foundation. And quantum seems to have been open source fairly so far. But how do you see open source communities shaping shared standards and trust in a more competitive landscape, a more mature market?
Yeah, this is a really interesting question that I think about a lot. I asked a question at a recent Unitary Con that had a lot of people working on open source software at a lot of different companies who are technically competitors. And I asked, like, what would your day-to-day work look like if all of us worked at the same company? And I think it's an interesting thought experiment because there is plenty of duplicated infrastructure, right? You have a lot of companies that do, they're doing open source development, but in practice, in many cases, it's kind of more of a develop in public kind of approach. Like, it's not necessarily the broad user community who's like deciding the roadmap or deciding, okay, across all of these different industries, people who work on different types of devices, like, we're going to come together and decide like what the Qiskit roadmap should be. Like, that's not really how it works. And of course, it makes sense, right? Like, each of these open source platforms are associated with a particular hardware modality in most cases. And trying to understand which pieces of these can be shared infrastructure, can be modularized to the point that we're able to actually use them across, say, different hardware modalities. I think that's a really useful area for open source. I think something like the Jeff Bridges compilation sort of exchange format. I think that's a useful direction. These more intermediate representations that are both usable for people who are not compiler experts, because anybody who has tried to get up to speed on like MLIR or anything like that recently, it's a hike. It's a hike if you're coming from the physics background. But actually understanding these types of abstractions that do allow us to actually move across different architectures is, I think, going to be really, really useful for that. And I think that's where Unitary Foundation is really well positioned to host, exchange formats, intermediate representations, and bring together people who are working on different types of hardware, different types of optimization and compilation routines into kind of modularize it and make it easier for everyone to use.
When we talk about at least scientific discovery, right, one of the core problems, not just in quantum computing, but beyond that, is being able to reproduce experiments, right? You have that's data, methods, as well as how you ultimately ended up actually implementing in the results, right? So I see open source as exactly the way you framed it, Jordan. Like, what if we were all working at the same company, right? I think that is one of the main reasons, at least, we have a lot of our stack being open sourced specifically for that, because you get to have a look at what people want to do versus what they're able to do. That's a wide chasm, as well as, you have people that would want to actually collaborate that wouldn't have been able to with just solely proprietary software. I mean, when you combine both of those things, right, it means that your iteration cycles are faster and faster. I had this one example, we've been working with Recon for that sampling-based diagonalization method, right? That work became open source, and then you had other organizations, Lockheed Martin, Cleveland Clinic, etc., creating their own novel, awesome experiments based on that. That also became open source. Take a guess what happens next, right?
Yeah, and I think one thing to keep in mind is, because I also teach, so I'm in a very complex point of, when I teach, it had to be open source because no one's going to buy very expensive access to systems or software, et cetera. But at the same time, I'm managing a company, I run a company, so I need to kind of have proprietary things, patenting, and et cetera. So I think from those aspects, what I've learned over the years, just having worked many years at IBM and then now on my own, is a couple of things. Is one, both of those communities need each other, right? Quantum started, the way it revolutionized everything, everybody's getting on board, is because we've all had access to it somehow without having to pay an arm and a leg for some of these systems, or having to work with a company that has it, but then have to work on specific types of problems. Open source, open access gives you access. It's the one, it helps. The big word is always in thrown out, democratizing it, right? You should have access to this and really use it and build your skills. I didn't come from any kind of quantum or physicist background. I looked at quantum. I loved the quantum when I was taking in college. I took a chemistry course. My professor talked about quantum. I asked, "What is there?" I asked, "What are these computers?" And I said, "You're not going to see it in your lifetime." Lo and behold, a few years later, we have one. So it's a bit of that. And on the proprietary, it's just, you work for a company, or if you manage a company, you're on that realm. Obviously, somebody's got to pay the bills. So there's that aspect of it. But there is that nice in between of something like called the Open Invention Network, I believe it's called, OIN, where big companies put their licensing, they license out basically for this open community to use. This is why you have things like open source using things like products and features that are available in proprietary, but they make it available just because open source also helps build the innovation.
Awesome. Thank you for that, Robert. And as we're seeing hybrid quantum classical methods being more of a standard now, how do you envision quantum software changing to accommodate for a truly seamless CPU, GPU, QPU workflow?
That's a good question. That's $1 million question, I think, right? Well, you guys are definitely on the right path. qBraid is fantastic. I mean, I was just telling them when I actually met Kenny a few weeks ago when we were in Uruguay. I was just looking when we used it for the summer school. If you guys all attended or tried a summer school, it's the first time I had it exposed to it, used it. It was great because it gives you access not only to have everything already set up for you, which sometimes is very difficult to do with dependencies, etc., but you can also modify things. So I think a lot of it is the simplicity, the access, the capabilities that you can build on top of that, right? And so with that, that does help bring people on board, helps simplify the teaching, educating, or even collaborating, because you're not worried about, well, what version are you using? What version are you using, which is a problem for us developers usually, right? I share my code with somebody, they don't like it, they got a different one, slightly different version, something's broken. So from that aspect, it helps out in that component. Now, when integrating with other systems, QPUs, CPU, GPUs, this is where I think there's a lot more opportunity in these aspects because there isn't much tooling for it. How do I, as a high performance computing, director or even just researcher, think about, okay, I want to offload some of this work from a high performance computer onto a quantum system. How much is that going to cost? And I don't mean cost like am I paying for anything. Cost as far as like what is the performance degradation going to be in order to do, because there is some overhead, right? And quantum isn't yet real time where I'm running it and I'm getting the same speed I do here. High performance computing platforms and infrastructures, nanoseconds or years, right? It's got to be, so what is the value? If I offload it, am I getting better accuracy? Am I getting better speed up? Or am I reducing the amount of energy that I'm using? Energy is a big problem nowadays, right? So having the tooling to be able to do that and integrating all of those things is very, very important. So those are things that people are kind of working on now, but it's still a big gap. I mean, if you think about it, people that are building quantum networks and quantum sensing, which is outside of quantum computing, if you think about it, if I'm looking at the entire workflow and I'm leading a quantum sensing team, I'm saying, listen, somewhere in this pipeline, there's a quantum computer, or there's a platform leveraging QPUs. What can I do now with my sensor systems, with my and systems here and just in general to be able to put into that workflow and optimize that integration into that? That's, I think, what we're looking at doing something next.
So I had shown that framework that we use that at least to help navigate what is the anatomy of an algorithm, right? This Qiskit pattern, right? And in that you have these 4 steps. Like you want to map your problem to circuits and observables, something a quantum computer could understand. You want to optimize it for that target hardware, run it on it, and then do post-processing, right? Each of those steps, right, just for the sake of argument, right, require different things computationally. Some might require, mapping might require CPUs and GPUs. Transpilation, same thing, as well as possibly QPUs if you want to do characterization ahead of time and modeling. You run it, then post-processing, right? There's requirements across CPUs, GPUs, etc. That workflow, right? That workflow is requires in it alone requires CPUs, GPUs, QPUs, right? You need to. How do we see quantum software evolving? It is being aware of that workflow, its needs, and being able to orchestrate based on the different types of resources across all of those, right? And I will say, right, that workflow is sure a microcosm of a larger experiment that somebody is doing, or a larger workflow, right, where you might need some pre-processing before you can actually do that part, or you might be running each of these in multiple batches. Quantum software to run across all of these things needs intelligent resource managers and orchestrators. And largely that's kind of some of the things that we're trying to sort out with some of the partners that we do for serverless and elastic compute, as well as for high performance computing like Robert mentioned.
I'll just briefly add, I think when we start talking about quantum advantage, it becomes very loosey-goosey in the realm of talking about orchestration between high-performance compute and quantum, with this kind of idea that, okay, like we'll just be able to plug in the quantum computer here and then the HPC here, and like I can draw this architecture diagram and it all fits together. And it's like, okay, well, is there actually any reason to suspect that using a quantum computer in that architecture box is going to give you anything, or going to give you an advantage over whatever the best known classical method is? And I think your question earlier about access and about people who are not physicists trying to get into the field and understand what its capabilities are is an important part of that. Understanding like, oh, well, you're comparing it to an algorithm from the 60s. So like no one does that anymore. I know that because I'm like the sysadmin for this HPC cluster and I'm constantly talking to scientists who do all this, like those types of conversations that they think really need to start happening more in order to understand that. And I mean, it's exactly like the professor was just saying about more teams being needed who have this genuine, like deep subject matter expertise on the application side and on the quantum side, and get more conversations that are, let's say, kind of like tribal knowledge, or like the types of things that you don't necessarily write in a paper, but everybody in the field knows. You kind of only get that with a real in-person collaboration.
Yeah, all really, really, really great points. Seeing that we are at a time now and dinner is just around the corner, I'll have to cut us short here. But I want to thank you, Jordan, Serket, and Robert, for joining us on the panel here today. Thank you so much.
Pleasure.
And we look forward to hosting you in 2026. Thank you all.